Welcome everyone to another session of the Data Science Summer School. My name is Hui Dang, and I'm the manager at our Data Science Lab here at the Hertie School. The Data Science Summer School is our annual effort to contribute to the open source communities by opening up scientific learnings for the general public. And we're very happy that to see so many of you here today from many different industries and disciplines joining us for the workshop in the last week or so. Our summer school is made possible by the support and fundings of the Hertie School and the Dietrich Schwartz Foundations in Germany. And we're very happy and we'd like to thank them for the continuing support. Our session here today is hands-on transformers, fine-tune your own BERT and GPT model, which will be a very exciting and practical sessions on how you can train your own data to create large language model. And the session is led by Moritz Lauhe, who is our associate researchers in the Global Governance, Regulations, Innovations, Digital Economy Unit at CEPS, which is a leading think tank on EU affairs in Brussels. He also co-organized the European Policy Data Science Network, a network of data-driven researchers in leading think tanks and civil society organizations. And beside his work for CEPS, Moritz also is pursuing a PhD in supervised machine learning for political text analysis at the Free University of Amsterdam. And he's currently also a visiting fellow at the Hertie School Data Science Lab. And also he's a very famous model builder with his language models on HuggingFace already been downloaded, I think, for over 400,000 times or something on HuggingFace. So he will share with us today on his experience of building these models and how perhaps to make it fun and exciting for everyone. And Moritz, the floor is now yours. I hope everyone will join the session today. Thank you very much.
Perfect. Thank you very much for having me, and thank you for the nice introduction. I really look forward to the session. Let me start sharing my screen so you can see my slides. Okay, great. Today in the session, we'll really take a hands-on approach to transformers. It's really supposed to be a very practical session on working with models like BERT or GPT or similar models that you've maybe heard of before. These models are all over the news, like ChatGPT and other models. Everyone has heard of them, maybe read a bit about them. If you follow recent developments today, the landscape for sort of developing these models might look something like this to you. So for David and Goliath situation, where there is Goliath, a few large companies like Google, OpenAI, Meta, Microsoft, and so on, and maybe a few elite universities with sort of enormous financial resources to build cool stuff. And then there's the rest of us, people with limited resources. I really hope that at the end of this workshop, you will believe, like me, that reality does not look entirely like this. The main tool for people with limited resources who want to work with these kind of models is open source tools. And with these tools, you can build really amazing stuff. Like 5 or 6 years ago, it would have required a team of senior researchers and several months of work to implement one of these models. Today, you can learn the basics and train one of these models within 4 hours. And that's what we're going to be doing today. So I hope you look forward to this. And the whole idea of this session is to empower you to work with these kind of models. Before we start with this, let's first briefly look at a bit about myself. I'm Moritz, so hi. I studied different social sciences. Then in 2018, I started programming first as a hobby and then later for work. As we said, I worked in the private sector, in a consultancy, and then in a think tank. Then I noticed when I work on this kind of stuff over weekends and a bit during the job, I don't have enough time to learn this properly, and I wanted to go a bit deeper, which is why I started a PhD around 2 years ago at Free University of Amsterdam, where sort of the focus or my main research interest is making supervised machine learning better with less training data. And another thing that I do on the side next to the PhD is I do some NLP consulting. That means I help organizations, I help companies implement these kind of models and sort of distinguish between what is hype and what is actually useful for them. And I also do open source contributions. I upload them on a hub called the HuggingFace Model Hub. I'll talk a bit more about this later. And the models have now been downloaded more than 20 million times, actually. It's mostly on zero-shot classification. Later on, I will share code, which I've also used to train my models, which hopefully then after these 4 hours, you will be able to build something cool yourself. Then, oops. Let's look at a bit of an overview of the different aspects of this 4-hour workshop. First, we do an introduction. That's what we're doing right now. Then we'll take sort of a high-level overview over the NLP Toolkit. There I will show you, especially to the beginners, how in 3 lines of code, you can run one of these transformers. And I'll show you how easy it is to work with these models today. That will be in a Google Colab notebook with concrete code examples. Then we'll go a bit more theoretical. We'll have a few slides on transfer learning, which is sort of the key idea behind these models that makes them powerful, I think. And we'll compare a bit different types of models. Then we'll go into the code again, and we'll go inside transformers, so inside of the main components of these models, the model itself and the tokenizer, also in HuggingFace, to give you a bit of an idea what the main components are. Then comes probably the most interesting maybe part of this session is fine-tuning one of this model, and there we'll have the full pipeline from start to end, from choosing a data set, choosing a model, hyperparameters, different metrics for evaluating it, and then also fine-tuning your own model. And if we have time, also uploading one and sharing it. Then we'll take a break. And then we'll look at essentially the same data set, but with a slightly different model, which I'll explain a bit more later, BERT NLI. Then I will have talked a lot about models and how we can optimize these kind of models. Then I also want to take some time to look at data. And so the headline for this session is Data-Centric AI, where we'll see how there is actually surprisingly much data noise, so bad data, also in very established data sets. And I'll show methods for automatically cleaning these data sets, and also a free annotation interface in case you want to set up your own annotation job. I'll share how to do this with a free annotation interface called Ragilla. Then towards the end, we'll then also fine-tune a generative language model. And we will also discuss risks and opportunities to these models, which is, I think, always important to be conscious that there are risks associated with using these models, and we will discuss these risks. And we'll end by looking at opportunities and concrete projects that you could start working on yourself after these 4 hours. And that's the whole point of this workshop, to give you code, which then you can use to maybe implement your first small project with a transformer. All of the materials for this workshop are on GitHub. This is the link to GitHub, and I will also post this now in the chat and also show there's a lot of things in the chat. If there's something important, please let me know. So here's the link to the GitHub. We also posted the link to the GitHub. Let's actually look at this together. Oops, that here. For those who are not so familiar with GitHub. So here we have all of the resources. That's 7 different notebooks. We'll go through them step by step in this course. Also, the slides are here, so you don't need to take screenshots or anything. You can look at the slides. You can open them now while I'm speaking, go backwards, go forwards if you want. So the slides are also already here. Then you can either, there's sort of 2 general ways of how you can follow this course. Either you just look at the screen. I will always share my screen, and talk about what I'm doing. That's maybe the best way of following. On the side, you can also open each notebook yourself and follow the code yourself, especially if you're a bit more of an advanced user. So you can open these notebooks, for example, the first one, then each notebook will have a button here called Open in Colab. You can click on this, and then this will open the same notebook in a Google Colab notebook. And then you can run this in your browser. You don't have this headache with setting up stuff, installing stuff, and so on. I understand that you've already used Colab notebooks in this workshop, so I'm not going to talk much about this. But this is what I recommend doing for everyone for each of the sessions. We'll come back to this GitHub for each session. You click on the notebook, you open it in Colab, and then you can follow along if you want to. Okay, this is sort of the general logistics, if you wish, of the workshop. I want to take this opportunity to briefly ask if there are any initial questions that you would like to ask. Maybe my audio is bad, maybe something is unclear regarding the general setup, which you would like to ask now before we sort of go into the content of the workshop. Are there any clarifying questions at this point? Cool, I don't think so. So let's move directly to the next slides. To the first part of the workshop, the open source NLP toolkit. For this, as I just said, we will go into this notebook that I've just shown, and I asked you to do this now. And there I'll show you the software and hardware tools for becoming David. So without much resources, do some cool stuff with transformers. And I will, for this, I will actually briefly stop sharing and share a different screen so that you see the Colab yourself. A large part of this will be me showing code and you being able to follow along. Okay, so you could go on this, click on Open in Colab, and then you can open it yourself. Okay, the structure of this first session is we'll look at the open source ecosystem, both the software and hardware, with simple code demonstrations. At the end, there will also be an exercise and a Q&A. Before we dive properly in, I also want to briefly address who you are and what your profiles are. So I understand that the overall cohort of people that are in this workshop where 36% of you have prior coding experience, so know some coding. 39% of you have said that they have a little bit of coding experience, and 25% have no coding experience. I understand that this is for the overall cohort. So for this advanced session, I think people probably know a bit more, but this is the overall picture. Some of you know Python, some know both, and the minority knows other languages like C++, JavaScript, and so on. This workshop explicitly tries to be useful to both beginners and more experienced participants. A few words to both groups, though. For beginners, there will be a lot of code shown in this workshop, and you will probably not understand every line of this notebook. That is fine, though. For you, especially if you don't know coding, the main learning objective is to get a general feeling of how much you can do with just a few lines of code, and that's actually not as daunting as you might think. Some people might think you need sort of a PhD in maths or something to do deep learning. That's simply not the case. And this is what I want to show you to motivate you also after this workshop to dive deeper. And there will also be sort of interactive parts and slides and so on, so it will not only be code. For more experienced participants, keep in mind that not everyone is as experienced as you, and we're all here to learn, and things will get a bit deeper later throughout the course. Okay, so then let's start. The open source machine learning ecosystem. Software look like today, so the software side. a key driver for progress here is the open source community and the open source ecosystem. One prominent example for this is HuggingFace, which is essentially a platform for sharing models and datasets. They provide one of the important libraries for this called Transformers. That sort of provides an easy to use way for using really the very latest transformer models. They also have a model hub where yesterday it was 300,000 models have been uploaded, trained by NLP researchers from big universities, very large companies, or from anyone who wants to, essentially. They also have a datasets library, and they host more than 55,000 datasets, and they're sort of the de facto open source standard for sharing and using transformer models. Besides other libraries, there's others like PyTorch and TensorFlow, but these are for a bit more advanced users. So for this, let's actually look at the HuggingFace hub a bit, and you will also explore this later a bit more yourself. So this is what the hub looks like. I remember when I saw this for the first time, this was a bit like Candyland for me when I discovered how many cool things are online and can just be downloaded. These are these over 300,000 models, which you can browse in a categorized system way like this. So you could, for example, say, I am interested in machine translation. And then you'll find 2,000 models that can do machine translation open source. So you, in a way, you don't necessarily need Google Translate anymore or paid services. You could download these models, run them yourself, and they will do pretty good machine translation. Or you might be interested in sentiment classification. Then you go on classification. And you again find a list of different models. You can sort them by trending, by most downloaded. And this is how you can sort of explore this hub. Okay, these are models. What is also, of course, important for these models are datasets to train them on. There we have the same category system and more than 55,000 datasets that you can download in just a few lines of code. And now let's maybe click on one of these models. That's not a good example because this is a model where you need to agree to terms of service to use it. Let's actually click on one of my models to give you an example for how these models in the ideal case are documented. So this is my most popular model, and this is a so-called model card, where you ideally the person who uploads the model writes a bit of a description on it and tells you what it can do. So here I describe on what kind of data this is trained, then some copy-pastable code, like you can just copy-paste to run the model yourself, and a few more explanations on the training data and so on. Here there's also sort of a hosted inference API widget where you can test the model in your browser. You can see what kind of things it can predict, what it can do. And this is how you can explore these kind of models, which you will do later as well. Okay, this is an overview of the HuggingFace hub. This is the software side. Then I think, like most people know now, there's also the hardware side that's important to running these kind of models. They require specialized hardware, these so-called GPUs, graphics processing units, that were originally created for gaming, but then sort of, I think that was a bit of a coincidence, were also good for training a specific type of AI model, and that have now become super in demand. And NVIDIA, the company that's producing them, has become extremely valuable because they're the main producer of this kind of hardware. You can't really buy this yourself. It's also very expensive. There are several ways of accessing them relatively cheaply. The main way of accessing this are, for example, Google Colab notebooks, where you can run code in the browser, essentially on servers from Google. So this is not executed locally on my computer, but on servers from Google. And I can choose different types of GPUs. So these are different types of GPUs that I can choose to run my code. For this run, because we'll run a larger model later on, I'll choose this, which is actually a very advanced GPU. This has not been available through Colab for a long time. It's really cool that it is now. This is essentially the type of GPU that most likely also GPT-4 is running on right now. Only that for GPT-4, they run this on more than 100 of these GPUs at the same time. We only have access to a single one. And you can only access this if you have a pro account, which I have, that costs like 10 euros a month. You can also run, except for one part in this notebook, you can run everything that I'll do today on this sort of a bit older GPU, which comes also with a free version of Google Colab. Okay. And then you know that there's these text cells and the code cells, and then you can run stuff in these code cells. Okay, now the GPU is initializing, and now we're running one of these advanced GPUs. Okay, let's start executing some code. Here I will show you how in just 3 lines of code, you can run these kind of models. The key ingredients for running them is 1, a model, 2, some input data. In our case, that will always be text, could also be images or sound or something else. And then thirdly, the model produces an output, which you need to post-process a bit. And I should also note, so this is a session on transformers. There are many different other types of deep learning architectures. Transformers are just the most popular right now. I will not go into the difference of these different types of models, because I think it's for our purposes not so relevant. This is the main algorithm that the most advanced systems are using today. But they might be not relevant anymore in 3 years. We don't know. Okay, so I run this code cell. And so for those who want to run this stuff yourself, you can now also start running the code yourself. Now I've installed different packages. That is the Transformers library. This is the main library from HuggingFace that enables you to run these kind of models. Sentence Beast, that's a tokenizer. I'll explain later what that means. I'm also installing a package to download text from Wikipedia. And for running the larger model later on, I'm also installing another package from HuggingFace called Accelerate, which makes it easier to run very large models and also theoretically run models on multiple GPUs at the same time. One thing that we need to do for running this large model later is, after installing this, restarting the GPU once so that something is properly activated. So I've installed this, then restarted the runtime, and now we can continue. Okay, now I will load the main packages. So here I assume that you've been to the Introduction to Transformers workshop last week. So I will not sort of explain the basics of Python. No, the introduction to Python last week, and I will not explain the basics here. Yeah. Okay, now there are 2 sections. Oops. In the first section, we'll look at models that are specifically tailored to specific tasks. This is how NLP was done from, I don't know, until 1 or 2 years ago. Depends a bit on how you count, and is also still done today. Or you have one model that is specialized in one specific thing. What we do here is we loaded a specific object from Transformers, which is called the pipeline, which makes it very easy in a few lines of code to run one of these models. So an example, let's first look at text classification models. We take the pipeline, we specify that we want to do text classification. Then we specify a model. In this case, I just took one from online from the HuggingFace Hub, which is from Cardiff University. It's a model that is trained on Twitter data, and it's designed to identify irony. So we will load this model. Now it downloads this on this server from Google. That just takes a few seconds. And then now we can run this model. Now we essentially have the model. Now I can specify a text, an input that could be, well, that workshop was totally worth my time. Then I run the model, or I take this text, take it as an input to the classification pipeline, get an output, print the output, and then I get a dictionary. Let's make this a bit prettier into a data frame. Now the model says that this sentence was irony with a sort of probability of 59%, and not irony with a probability of around 6%. So now in just these few lines of code, we run a transformer. Now the cool thing about this is I can take any other model identifier, which, by the way, I should show this. You can find like this. You go on the website, then you are on the page of a specific model. So you go on models, because you will need to, so this is important to pay a bit attention because you will need to do this yourself later on. We go on models. Then, for example, you might have heard of this. There's the Llama 2 model from Meta, which is online here. Then we can copy the identifier. This is the identifier. We copy this by clicking here. And then we can simply copy this, paste this here. This is how we find and load a model. For our purposes here, let's try another one. This is a model for emotion detection. So we left everything essentially the same. We're just loading a different model. I'm running this again, just takes a few seconds to download. And then we'll also take a different text. Whoops. So here our text is, well, this smells weird. I'm not sure if I should eat this. Yikes, that tasted like old socks. Let's say what emotion this model thinks was in this text. The scrolling doesn't work properly. So the model thinks that this is with a 40% probability disgust, with a 37% probability confusion, annoyance, disapproval, and you get a probability for each of the classes the model has learned. Okay, these were classification models. A thing that is specific about these models, and we will come back to this later, this is important. These models are, in a way, relatively stupid or limited. They can only do exactly one thing. They can only do exactly the task they have been trained to do. They can only predict exactly these classes. If you want to change anything, the definition of disgust, or want to add another class, you need to retrain the model from scratch. And that's a big limitation of these kind of models, task-specific models. Okay, now let's move to another thing that until recently you could only do with a service from a big tech company, from Google, Google Translate, or other companies, machine translation. So there are many open source machine translation models that are available online, which you can find via the hub. Again, you go here, you go on machine translation, and then you find different models with the different descriptions of what they can do. In this case, we're loading a model from Facebook, now Meta, that can do translation in 100 different languages, in all directions of 100 different languages. And here we take another text again. This is German. Ich bin ein Fisch. I specify the source language, German. I specify the target language that I want, English, and I get the translation as an output. The same also works for longer text. So here I'm downloading the Wikipedia article summary from Donald Trump. I'm specifying in English. So I set the Wikipedia language, download the Wikipedia summary of Donald Trump, input the text in the translation pipeline that I've initialized above, specify the source language and the target language, and I get the translated output here in just a few lines of code. And now this we can repeat for many different tasks, for text summarization, for textual similarity, and so on. So here we summarize this article with the summarization model. That one is a bit bigger. Actually, a good thing if you run stuff in Google Colab is that this runs on sort of Google's internet connection, which is pretty good. So we downloaded a gigabyte in 2 seconds, which is pretty fast. And now we have the 1 sentence or 2 sentence summary of this article on Donald Trump. Last example, token classification. Which the most prominent example for this is named entity recognition, where you have a long text and you want to know what kind of entities are mentioned in the text. So who are the people, the locations, the nationalities, the laws, or whatever that is mentioned in the text. Again, we can do this in a few lines of code. Pipeline, we want to do token classification. We specify a model. And then we have a named entity recognition pipeline. And we can analyze this article on Donald Trump, where we see that we found a person, Donald Trump. We found a miscellaneous entity. So this specific model cannot identify nationalities, American, a location, United States, another person, Trump, organization, University of Pennsylvania, and so on. Also in a few lines of code. Okay, so a specific thing about these models was, as I said before, they can only do one task. There are other models, universal models, that can do multiple tasks at the same time in a specific way, which is relevant because in reality, there might be 300,000 models on the HuggingFace Hub, but for the specific research question that you have or the specific business problem that you have, it's actually unlikely that someone has trained a model that has exactly the classes, for example, that you're interested in, especially if an academic and you need to have a specific theoretical definition of a category. Existing data sets and the existing models probably don't cover this. So you need something more flexible. And these universal models can partly, not entirely, but partly solve this issue. I will share 2 here and also dive deeper in them later on. And we'll also fine tune both of these types later on. One of them, these types of models, is so-called NLI models, which is based on a universal task called natural language inference. This one can solve any text classification task, but only text classification tasks. And then there are token generation models, so next word prediction models, for example, which probably most of you know. One example for this is ChatGPT. And these models are so universal that they can solve essentially any text-related task. The big price they pay is that they're huge and harder to run. Okay, let's first start with the NLI models, with the zero-shot classification models that can do any classification task, also for classes the model has not seen before. We do the same as before. We have the pipeline. We specify zero-shot classification. Zero-shot in this case means we need 0 training example for the model to start predicting, to take a shot at the task. That's what zero-shot classification means. We take a model, in this case, one of my models. This one is also a model that is multilingual. That's sort of indicated by the M at the beginning. And this one can do zero-shot classification in 100 different languages, so not only in English. That's in general a big problem in this field still, that most of these models work well in English, less well in other languages. This model also doesn't solve this, but it works also decently in non-English languages. So we've initialized the zero-shot classification pipeline, and then we can start classifying something. In this case, let's take a text. So this is a business use case I might have a text that comes from a consumer who says, I have not received my reimbursement yet. What the hell is going on? And I want to know, so if I want to triage messages that come into different categories, is this a payment issue? Is it travel advice? Is it a bug report? Then this is how I define the classes. I verbalize the class. I have the text. I put both of this in the zero-shot classification pipeline, and I get an output, or I get probabilities for each class. So here the model says that this is probably about a payment issue, 99% chance, and probably not about the two other classes. Now, the cool thing about these universal models is that you can add any other class formulated in sort of normal language can be added to the pipeline. So here now I just extended this task to more classes. Is it about opening an account or customer complaint? Let's see what the model says here. Now I get probabilities for different classes, 2 additional classes. Still, it's probably a customer complaint, probably about payment issues, maybe about opening an account. I also showed this intentionally because this is sort of a mistake of the model, because the text is not really about opening an account. It's not sure, but it has an almost 60% accuracy. So that would be a bit of a mistake. That is the disadvantage of these zero-shot models, is that they're not tailored to your specific task, which means that they're less good at it. So to make it better at this task, you would need to fine-tune one, which we'll do later. Another example, which is a bit more social sciencey, I could have a different text. Now I still reuse the exact same model, and I input a different text. I do not think the government is trustworthy anymore. We need to mobilize and resist. Now I know whether texts are about civil disobedience, phase of the government, or travel advice. And the model tells us that this is probably about civil disobedience. And again, I could add another class here, and it will also predict the additional class. Okay, these were zero-shot classification models. Now let's look at generative models, which are even more powerful. For this, a brief word on GPUs. So this is the one thing that you cannot really run with a free Colab. Let's check what kind of GPU we're running right now. Here we are running one of these A100 GPUs from NVIDIA with memory of more than 80 gigabytes of memory. That's pretty huge. We can also look at the thing here. This also costs. Costs like more than €1 per hour to run this, but it's a really good GPU. So for running this, I'll now connect to my Google Drive, because I will not download this model. I've done this before so that this is a bit faster. Just quickly connect to my Google Drive, where this is saved in a repository already. This is the path to the repository. I set the path to the repository so that we can just load the already downloaded model. What we will use here is a model from Google called T5, and a specific version of it, Flan T5, and sort of a larger version of this. I think the XL version is around 3 billion parameters big, so that's relatively big. Although you might know that GPT-3, for example, is much bigger, 176 billion parameters. So this is only 3, but already this will take like 3 minutes or something to load this into memory of the model now. It's a good illustration of the limitations of this. But we use essentially the same approach as before. Now we take one of these sort of complicated generative models. We just specify the name. We have the pipeline. We say that we want to do text generation, specify the model name, and then 2 specific arguments that sort of help us load smaller models. This one, for example, makes sort of the weights or the numbers in the model a bit less precise in a way, without sacrificing accuracy, makes it easier to run the model. Now this will run for a minute or so, so I'll just continue. Here I added a bit of a note. You can also read this later on hardware. So you will not really be able to run larger models than maybe 7 billion parameters on a standard GPU that you get via the free Colab. And there are different solutions for this, either better hardware, which you can get if you subscribe to a service. But for this, you then need to pay money. It's not super expensive though, depending on the service. Another solution, there are different software solutions, like lowering the precision or quantization. I'm not really going to talk about this now. It's not so relevant for an introductory session, but there's also ways software-wise to make these models run better on smaller hardware. So you can also run this kind of model that I'm running now also on your local CPU, actually. It will just be slow. And there's some advice in the HuggingFace documentation. I've put a link here where you can read more about this. And the last piece of advice when thinking about using larger models is maybe you actually don't need a larger model. Maybe a smaller model does it as well, which is, I think, something that, especially right now, people neglect a bit. When I talk to people, they always want to run or fine tune these big, I don't know, 30 or 60 billion Llama 2s or Falcon or whatever. While in reality, if you spend like half a day on annotating some data and you fine tune a smaller model, it will be just as good or better than the large model. And then you don't have this whole headache with hardware. So that's also something worth saying. So now let's see. Okay, so we've loaded this model. It took 3 minutes to load it. Let's see what this model does. In this case, now this is a bit I'm sure people have used of the ChatGPT interface, and this is a bit like this interface now. So I give it an instruction. For example, for text classification, if I want this model to do text classification, I could tell it, here is a quote. I do not think the government is trustworthy anymore. We need to mobilize and resist. The same thing I showed before. Then I ask the model, is this quote either about A, civil disobedience, or B, place of the government, or C, government-funded mobility? Only choose one of these options. Let's run this. The thing that the model will now output is not a probability of a class, but because it's a generative model, it outputs texts, it outputs words or tokens. And this is the sort of genius thing about these models, is that by translating a task into a text generation task, you can do essentially any task with them. So here it has generated the string, the text A, which we can map to our category, civil disobedience. So the model's prediction is essentially that this text is about civil disobedience, which would be correct. Now this was text classification. We can do this for other tasks too. Here I have a long text on, there was a news article from the BBC or Politico or something like this on an attack from Russia on the European Parliament with a lot of information. Now we want to ask a few questions about this article. So this is now a question answering use case, and with a bit of post-processing code, which I'm not going to explain now. And there we see the outputs of the model. Was there a cyber attack? Yes, no. The model says yes, which is correct. Who is the name of the attacker? It is extracted the string killnet, so it responds this. Which country does the attacker come from? Russia, which is correct in this case, and so on. So it could also do text question answering. Here now I'm going to go a bit faster. I can also do text summarization. I give it a long article and then say at the end, please summarize this text for me. I will do this as well, so on. Okay, so this was a lot of content. Now I want to make it a bit more interactive. Now we do a small exercise. for this exercise, I want you to go on the HuggingFace hub, click around a bit for 5 minutes, maybe a bit less. Look a bit at the descriptions of these models, and then open this Google Doc. I'll also post the link in the chat. The Google Doc looks like this. Some people are already in there. And then I ask everyone to sort of choose one of these empty fields and copy the identifier of the model here. For example, this is a machine translation model from Facebook, and then write just one sentence very briefly why this could be interesting for you. So for example, for this model, the reason why you find this interesting could be, I live in India, my native language is Telugu. This model seems to be a model that can do machine translation in Telugu. Or this is the emotion detection model that we've seen before. So you could write, I'm a psychology student and I'm interested in sentiment analysis. This model seems to be able to do this. Okay, so now let me actually post this in the chat. And now I'll give you maybe 3 or 4 minutes to go on the hub. So it's huggingface.co, browse through the different models, and then copy paste this text in here. Cool. And if you have any questions, let me know. I see a lot of things were posted in the chat. I'll also check this now.
Hi, Moritz. So maybe while everyone is looking at the models, we can go through some of the questions that were posted before.
Cool.
And there was one question that was asked by Jingya, which is about the work-to-vec package and sentiment analysis in general. The question is, how do we add the deep learning component into these other methods, and how we can perhaps use deep learning to make work-to-vec performance better, for example?
That's an interesting question. We will actually talk a bit about this later. The vectors, the word vectors you get from word2vec, you might know this, they can be input to a classifier. So this is a feature representation, a way of representing text as vectors that we can input into a classifier. We'll later discuss 2 things, and then I hope this also clarifies a bit more later. We will see that every BERT model actually has its own word embeddings. So BERT itself, and also GPT-4, builds upon the idea of these word vectors. We'll see this later. 1. We will also see that I think today, in most cases, I would not use word vectors anymore. What you can do today is you take not individual words, but an entire sequence, an entire text. And then there's something called a sentence transformer that creates also a vector, but for an entire sequence and not an individual word, which is sort of, in a way, the deep learning way of translating text into vectors today. I hope that was useful.
Yeah, thank you. And the second question is regarding these NER recognition models, are they language specific? Jacob asked questions because you see that English was very specified for the source of Wikipedia page, but not for the dictionary to recognize the entities. So would the same models work for the same way in other languages as well?
So that depends on the model. There are most NER models that you will find on the hub are English language models, but there are also multilingual ones. So the way you would find this is you go on the hub. I should share my screen again. But you can also, it's not difficult. You go on the hub, you go on NER, and then you also specify a language, or in the search bar, you type in multilingual, and then you will also find multilingual named entity recognition models.
Thank you. And another question is regarding how do we find the first parameters of the pipeline from HuggingFace? I think this is more about the examples, right? For
There is documentation on this. I hope I put this into the I'm actually going to briefly kill my session here because that's a bit expensive. If you read through at the very beginning of the pipeline, yeah, I will post the link in the chat, and there you find this. I just posted in the chat. Other questions?
Yes, the next one is the probability outcome based on the old data. So I think this is from the code within the code lab that you showed earlier.
On the old data, I'm not sure if I understand correctly.
I think it's the probability outcome for the classifications that was mentioned earlier.
It is always based on let me share my screen, on the text above. So the probability for this, for example, is the output here. Here we have the probabilities that are printed here are built based on this specific text. I'm not sure if that answered the question.
Yes, I think that's the idea behind the questions. And the next one is, could the model predict several languages at the same time in a larger data sets?
Yes, the multilingual models, you can give them a batch of 100 texts with 50 different languages. And if it's multilingual, it doesn't matter what the proportion of models of languages are in the text. So yes, for example, the multilingual zero-shot model, you don't need to separate them in different batches in different languages. It does this on its own.
Great, thank you. And another question is regarding Susmitha asks, would we be able to build transformer models rather than downloading it from HuggingFace? So I don't know if this is related to just building it natively and not having to use a HuggingFace model.
So that's also a good question. We will not cover this in this course because that is more advanced. That is actually more complicated. This you will not be able to learn in 4 hours. For this, you either use PyTorch or TensorFlow, which are specific other packages we will not cover today.
Yes, and the follow-up is, does HuggingFace get the source code for the model?
For the model, you can find in the internal code base, everything is open source, so you can find all the code. You also see how they are loading it. What they mostly do, if Microsoft or Facebook or someone else publishes a model, they publish it on GitHub. Microsoft publishes it on GitHub. Then someone either from the open source community or from HuggingFace writes some additional code that translates the code from Microsoft to the HuggingFace code. But everything is always open source.
Thank you. And Victoria asked about, she's working with blind people and they get information from the internet in articulated text from their devices. And many pictures on the internet are not accompanied with picture description. So it's basically a big chunk of the internet is inaccessible for the blind. And so she was asking whether or not specific models on HuggingFace could work with this, which is an image captioning models.
So I don't know much about working with image, because I specialize in text, but yes, this exists. So go on the hub, go on image to text, where the input is an image, the output is a text, and then browse through it a bit. And there are models from Stability AI, from Microsoft, Salesforce, other organizations that do exactly this. I don't know, but I'm relatively sure that you will find something on the hub.
Thank you. And Mingma asks, I find one problem of using LLM is to classify text that I use the same prompt, but generate not the same format for all classification results. Sometimes it generates class that we set, but sometimes it generates its own explanations. How do you explain that?
So this is prompt engineering with, you're probably using OpenAI or maybe open source models. We will talk a bit more about this later when we come to fine-tuning a generative model. There, the main thing that you need to tweak is the instruction that you give the model. And there, so if it depends on your use case, so I cannot give you a perfect answer now, but it would be, especially, I think the main practice is giving it 2, 3, or 10 examples in the prompt of what the output is supposed to look like, maybe 3. And then I also always add at the end, only respond in JSON format, or only respond in exactly this format, and maybe add an exclamation mark or something like this. And that makes it more likely that the generative model outputs exactly the format that you want. But that is a disadvantage of these models, especially the smaller open source models. They will do this. It's simply also a disadvantage of generative models.
Thank you. And the last question is how the training data sets will look like if we need to classify the text with the mixtures of 2 languages at the same time.
The training data set will look exactly the same. Well, you should probably do a bit of post-processing and so on. But I will, if you take a multilingual model and you want to find, so it's pre-trained in a multilingual way. We'll talk also more about this later. It's pre-trained in a multilingual way. If you want to then fine-tune it, say, on 2 languages, you have a data set, could be a CSV file, an Excel file with 600 texts in one language, 500 in the other language. And then you shuffle them so that they are in a random order and the languages are mixed. And then the rest is actually literally the same. So there is not much more specific that you need to do. The main thing you need to do is loading a multilingual model. And we'll also come to this later.
Yes, and we have 2 more questions. One on YouTube. Do you have any recommendations for sentiment analysis models, specifically on polarity for text like a news editorial?
Oh, okay. I think the honest response is no. No. I would go on the hub, type sentiment or polarity or emotion, see what is there, see if there's something that's close. In general, I am a bit skeptical of the existing sort of sentiment data sets that are out there. I think it's unlikely that it's going to cover exactly what you will have to, what you want to do, your definition of polarity. So you might have to fine tune something yourself. But if you don't need to be, if it's not academic, you don't need to be so accurate. Search here, but I don't have a specific one in mind, unfortunately.
Yes, and this is probably the last questions. So Ishita asked, what are some of the best way to perhaps evaluate LLMs? She wants to compare different LLMs and prompts, but they don't know how to compare them because they use private enterprise data with LLMs. So I think it's more about evaluation process and maybe scoreboards on these open source models.
I think here I'll just respond briefly that we will cover this later. Evaluation of models, metrics for models. So bring this question up later again when we're in that section. It's a very good and important question.
Thank you.
I think we actually need to, perfect, very good. We should actually move on, which it's actually great that you asked so many questions. I wasn't sure how many questions people asked. You asked a lot of questions, which is perfect. You did hopefully the exercise at the same time. Okay, perfect. This is super full. It's amazing. Won't read this now, but you can also get a bit inspired by what the others wrote. And the point of the exercise is for you to explore the hub and think a bit about this. And here are a few more things that you can think about if you want. But I think we've now extensively covered sort of the different questions that you have, and we should move on to the next section. Okay, let me share my screen again. Oops. Now we will do a bit more of a theoretical part on, there it is, on what transfer learning is, this thing behind these different models, what makes them work so well. Okay, this is what we just did. Now we talk about transfer learning. It's always good to check time a bit. We are actually behind, so I'll speed a bit up during this part of the session. Why are LLMs so powerful? There are many reasons for it. It might be the size of the models, the attention mechanism, which is a specific thing that sort of defines transformers, the many different layers or other technical things about these models. The one thing that I want to talk about today is transfer learning, which is sort of the general idea that makes these models work well. What is transfer learning? Transfer learning is storing language knowledge and task knowledge in the parameters of a model to learn new tasks faster and better. If you know a bit about sort of older methods, there are methods like regression or support vector machines, what people used before transformers. Their main limitation is that they have neither language knowledge nor task knowledge. So they have no prior knowledge of, for example, now I'm on the left side of the slide, of semantic similarities between words. For example, a regression or a support vector machine in the beginning does not make any difference between the word attack, war, and tree. It's semantically exactly the same for the model. It also doesn't know anything about tasks. It cannot do any task yet. Support vector machines can only draw lines into space. It cannot do anything useful. So it cannot do a task like classify this text into 2 categories. This is the key limitation. The first limitation, language knowledge, was first addressed by word-to-vec, word embeddings, which we've heard about in a question before. Which is a way of representing semantically similar words in similar static vectors. And a vector is just a sequence of numbers. So this is literally an example of a vector. For example, I've invented these numbers, so this is just for illustration. Word vectors represent, for example, the word attack as numbers like 0.1, 0.8, minus 0.5, 0.1, then similar words like war that are similar in the sense, and this is everything the model learns, that these words appear often in similar contexts, often next to each other. These words are represented with similar numbers, similar vectors. So for example, 0.2, similar to 0.1. This might be the same number, this might be similar, this might also be sort of similar. While other words are represented with dissimilar numbers, like the word tree has a dissimilar vector. This was sort of the first thing, 2013. Then came different architectures, among them transformers, for example, BERT base, which also has this representing words with similar vectors. The additional thing that BERT can do is representing the same word differently if it appears in a different context. So we can have the word capital, and it has a different meaning if it's next to the word city or investment or crime. It's actually very different meanings, and BERT can represent this internally. What does this look like on a very high level? So this is the general architecture of BERT, very simplified. We have an input text in the beginning, capital city, traveling recommended, some word. We feed all of these words into the model. In the model, every word is then already represented as a sequence of numbers, as a vector like this, which is a static word vector, essentially. Then each of these vectors, so in this case, this is the vector. Then this vector goes through the neural network, and this is sort of where the magic happens and where the transformer thing happens, the so-called attention mechanism, where this vector is of, for example, the word capital. This represents the vector of the word capital, is multiplied in a specific way with all of the vectors of all of the other words. That means this vector pays attention to all of the other words. This is the attention mechanism. Also, the word city is a vector here and is multiplied with all of its surrounding words. That happens in one layer, then in another layer, again, everything is multiplied with each other, so that at the end, you have, again, sort of a word vector, but here, the vector of the word capital, in this case, now is sort of adapted to the context. So here it's of a geography context. So here the word vector is more similar to sort of geographic context. This is of the innovation of models like BERT. How do they learn this? Through a simple self-supervised task called masked language modeling. A self-supervised task means this is a task that the model can learn on its own without someone having to label stuff for the model, because it's so simple that no labeling is needed, no human intervention is needed. What does this look like concretely? This is a sentence, I copied this from Wikipedia, on capital punishment, on the death penalty. Capital punishment, also known as the death penalty and formerly called judicial homicide, is blah, blah, blah. What we do when we pre-train BERT, when it learns its language knowledge, is we take around 15% of all of the words and we hide them from the model. We put a so-called mask in front of the model. Then the task that the model learns and that we give the model is to predict the actual word that was behind this mask. So here it's supposed to know that in this context, behind this mask, there's supposed to be the word punishment. This is how it learns some knowledge about language, which words appear in which context. And then this happens many times. You give it an input with masked text. It goes through the models with the model. At the end, you show it what actually was behind the mask. This runs for days on a GPU. And then all of these parameters, all of the many different vectors that are in this model are optimized for this specific task, predicting hidden words. Now, the main disadvantage of BERT is that it only knows predicting hidden words. It only knows this masked language modeling task. In reality, we're not really interested in this. We want to do something like classification, summarization, translation, and so on. Every new task, BERT needs to learn from scratch again. It does not have task knowledge. It only knows something about language, but not about tasks. There's a way of addressing this issue, and this is now sort of more advanced transfer learning. There is universal tasks. These are tasks that are so general that we can translate many other tasks into this universal task. Okay, the first one I'm going to talk about, and this is what my research focuses on and what the models that I'm publishing mostly do. Natural language inference. What is natural language inference? We have a text. We call this a context sentence. That could be, for example, the EU betrayed its partners during the negotiations on Sunday. Then we have a hypothesis. For example, the EU is trustworthy. The NLI task is now to determine whether this hypothesis is true, false, or neutral, means we cannot say, given only this text. So it's not about determining whether the EU is trustworthy as a general matter of truth or something like this, but only given this context sentence. This is the definition of NLI. So what does this look like concretely? This is what we feed into the model, the same text, a context hypothesis pair. Then the output that comes out in the end, after training the model on this kind of training data that has context hypothesis pairs, is a probability that, for example, in this case, the hypothesis is false with some probability given this context. Now, the interesting thing about this task is that you can translate any other classification task into this universal task format. That means, for example, we have a sentence like, the ruble plummeted amidst a surge of investors withdrawing from Russia. Then I formulate two hypotheses. First, the economy is performing badly, or the economy is performing well. And so this is everything formatted as an NLI task. What I'm actually interested in this hypothetical scenario is I want to do a classifier that identifies whether the economy is performing well or not well. Now, NLI cannot do this specific task, predicting good or bad, well or not. What it can do, is that it can tell us whether this hypothesis is true, false, or neutral. And it can tell us whether this hypothesis is true, false, or neutral. What we can then do is we verbalize our labels, our task in these hypotheses, and then look at which of these hypotheses is the most likely. And then we assume that this is the correct label. So in this case, in this sentence, the economy is performing bad. We can do that with many different tasks. For example, the politicians are bribed by lobbyists, and then I can formulate sentences. This would be topic classification. It is about corruption. It is about peace. It is about the free market or something like this. And then at the end, I choose the hypothesis that is the most true. And this would be my true label. The main advantage of this NLI task is that it's a very data-rich task. So there are many datasets with more than 1 million annotated sentences that you can download online. They have a permissive license. And then we can train these kind of models on this. And this is research that I've done. And on average, BERT base, the green line here, if you have below, let's say 2000 data points, is worse than BERT NLI, or BERT NLI is better with less training data, and BERT NLI also with 0 training data. So this is accuracy with 0 training data, already can perform the task. This is zero-shot classification. Then we can fine-tune it, for example, on 100 texts or 500 texts, and it gets better and better, faster than BERT base. This is an example for transfer learning with NLI models. These models also have relevant limitations. They can only do classification. And it's only worth it to use it if you have, let's say, more than 1,000 or 2,000 texts. Otherwise, BERT base is better if there's enough text to learn the new task from scratch. And it cannot do something like summarization, translation, information extraction, and so on. An even more universal task that pushes this idea of transfer learning, of storing language knowledge and also knowledge about many different tasks, is next token prediction or next word prediction, which is the main task behind the GPT models and other models. Also a self-supervised task, which is an advantage over NLI as well. So it can learn this from without training data. What does this look like? In this context, quickly checking the time actually. Okay, in this context, we could have a text, capital punishment, also known as the death penalty and formerly called judicial homicide is. And then what GPT does, it gets a part of this text, but it's cut off at a certain point. And then the task for the model is to predict the next token given all previous tokens. So I get this text, we put it into GPT, and then we know what was actually here. And we wanted to predict that the next correct word is as. Then we feed this into GPT again, and we want it again to predict the next word. For example, here, the. This is what the model can learn from text without supervision. Now we can translate any task into this format. I do this faster. We've seen this before. I can have a long text. Then I can ask, is this text positive or negative? And then we ask, what is the next plausible word? And if the model is tuned properly, it will predict the word positive. For a classification task, for example, we could ask it to extract information, a list of countries, for example, to summarize text and so on. This is how you can translate any text as understanding task into a token generation, into a text generation, word generation task. Okay, this was sort of a rush through transfer learning and how we can accumulate both language and task knowledge in models. what I want you to do now, one, I will check the text again, the chat again, and answer a few questions. You can also look at these slides. I've wrote down a few questions and just take now maybe 2 minutes, and you can think about the questions that I've put here. And any questions that come up, also when you look at the slides, as I said, the slides are online. You can also download them and look at them again. Any questions that you can have, just post them in the chat now, and I'll try answering. I think now we can sort of do this simultaneously. So you can think about these questions there, or post the questions in the chat. Let's collect a bit more. I'll wait like maybe a minute or so, and then I'll answer the questions. Okay, given that we're a bit behind on time, I'll start with responding to the first question. Do you have some literature recommendation for studies investigating the correlation between training data size and performance? Or are there some general rules on how much training data is needed or till when the performance of a model is good? Yeah, that's several questions, and they're very good questions. And people ask this a lot, especially how much training data is necessary to train a good model. What I would recommend for this is one source for this is the paper that I wrote. There will be a link to this later on as well in one of the notebooks. You will see that link later. It's called Less Annotating, More Classifying and Political Analysis. And there I sort of show what performance you get as a function of training data size, essentially this, which gives you a rough estimation of how much training data you need for what kind of task. So this is actually on average across 8 different tasks. So I try to make it diverse, also tasks from different domains and so on. You can use this sort of as a rough idea of how much training data you need. But I cannot give you a perfect response because it depends on your task. Depends on how many classes you have, how complex the concepts are that you want to measure. So there's no one size fits all solution. I think with a good model, you already good performance with 1,000, 2,000 data points. Then you also need some models for testing. So you might need 2,000, 3,000. And you can annotate this within a day or two. And then you see whether that's accurate enough for you or not. Okay. Other questions? Are the zero-shot models always also available on HuggingFace? And are they always better? Yes, they are on HuggingFace. If you go here, models, zero-shot classification, and there are, for example, my models, that's other models. You can just download them. Are they always better? No, definitely not. They are only better if you don't have time or expertise or money for creating training data. If you have time and expertise to fine-tune your own model with, say, 1,000, 2,000 or more data points, then this will probably be better. So there's a trade-off between the amount of resources that you have and yeah, time and performance. Imbalance, there's one on imbalance. We definitely come back to this later, so I'll respond to this later. Yeah, Aaron posted my article. Exactly, that's the one. can transformer be both word embedding and BERT base? So BERT base does not have word embeddings exactly like word2vec. It uses a similar concept. So it also has words represented in the first layer in the vocabulary as vectors, but they were not done exactly in the same way as word embeddings. How do I create word embeddings? There's a library called Gensim. I'm not going to cover this here, but you'll find documentation on it online. I put the word in the chat. They are in Python. They are good for creating word embeddings. In R, I don't know, but I'm sure they're good packages. Okay, cool. Let's continue. Green. Okay. Oops. So where are we right now in the session? We talked about transfer learning. Now we go inside of transformers. So now we go in a notebook. So now I ask you to go into the GitHub repository again. Maybe someone can post the link again, and then we go into this notebook, the number 2 inside of transformers. This one. I'll switch this to a different screen again. Okay. So now let's take a look into transformers. That was a bit of theory. Now let's look at what this looks like if we translate it into code. Here we use, again, HuggingFace Transformers. For this, I wanted to explicitly say this. In this session, we run everything on a CPU because you can also run transformers, especially sort of models like BERT that are not huge, like the generative models. You can also run them on a CPU. So you should not think that you can only run them on expensive GPUs. Everything I do now, I run on a CPU. Install transformers, and we look at 2 main components, the tokenizer and the model itself. The tokenizer helps prepare the text in a clean format that the model can understand, because it can actually not process sort of raw strings, but tokens. And tokens are sort of words or subword units. So for example, in BERT's vocabulary, the word good is 1 token. So that's 1 word. While more rare words that don't appear so often are split into 2 tokens, like Darwinism is split into Darwin and ism. These are the words the model know. And then the models have a vocabulary of around 32,000 to 250,000 words, or these tokens that they know, for which they have a vector representation internally. The tokenizer takes a raw text and translates them into token IDs. So an identifier that helps them link the token string, the word, to the vector internally. And this is what the model can then process. Okay. So we've installed transformers here. Then here we load 2 classes, auto tokenizer and auto model for sequence classification. So this is this is therefore loading a tokenizer, and this is therefore loading a classification model for our example here. Then here we take a variant of BERT that was fine-tuned on a binary sentiment classification task, so it can say if a text is positive or negative. Then we'll take the auto tokenizer. We say from a pre-trained model that is somewhere on the hub. This is an identifier that you will also find on this hub. So these are these words. Now we load the specific tokenizer that's specific to this model. And we also load the model itself with these few lines of code. So this is downloaded now. And now I've put sort of into code words, or a combination of code and language, what happens with an input text. So walk you through it like this. And if you're interested, you can look at the code a bit more. So we have an input text. It says, I believe that the EU is trustworthy. The tokenizer then splits this text into the separate tokens. For example, the word trustworthy is not a very frequent word. So BERT splits it into two tokens, trust and worthy. For BERT, these two hashtags mean that it's sort of the beginning, or there's another word before, so it's a composite. The main advantage of this is that you never have a situation like with other models that BERT doesn't know a model, because if doesn't know a word. If a word is very rare, it will just split it up into A, B, C, D into its individual characters. So you don't have an auto vocabulary problem like with other older models. We can actually look at the vocabulary of BERT here. So this is from the HuggingFace Hub. These are all the words BERT knows. It's just a simple text file with Seattle, comics, prisoners, and lots of different words. This is what the vocabulary of BERT, or in this case, the SailBERT, a smaller version of BERT, looks like. Then this sentence is split up into the separate token. I believe that the EU, blah, blah, blah. Then the tokenizer maps this to different numbers. And these are the IDs that help the model link these words to the vectors. Looks like this. And then as a specific thing, we also add a class token, classification token in the beginning. This sort of represents the entire sequence, it's not so important now, and a separator token, which tells the model that this is the end of one sequence and the beginning of another sequence, so that the final input to the model looks like this. The model gets these sequences of numbers. For us, humanly understandable, this looks like this. Okay. Now, what does this look like when this is sort of fed through the model? You remember this network architecture that I showed of the model? What does this look like? And what does it mean when the model represents a word as a vector? So we input this into the vector. Now we look at the model, its embeddings, its word embeddings, and we look at the word at position 7. In our case, this word was the word trust. In the beginning, the first layer, as I said, the word embeddings, and this is literally the way that BERT understands or sees the word trust, a sequence of numbers. So this is what trust means for BERT. In the first layer. Then, as I said, we go through different layers, and these numbers are multiplied with the vectors of all other words. In the second layer, the numbers look like this. They are slightly different. In the next layer, they look like this, where the first number is different than this, and so on. Because there are certain multiplications that go on in the model, and that's how every word changes successively as it goes through the model. And in the end, we have a contextualized representation of the sequence, which is again essentially a bunch of numbers. This is what this architecture looks like. I'm going to skip this now, though. And then we get the final output. Ooh. Name output is not defined. Interesting, because I didn't run something as first. Okay. Let's run this also that it works. Okay, now at the end, the model outputs so-called logits, which for classification model, each logit represents sort of the probability of each class. So at the end, the fine-tuned model, in this case, a binary sentiment model, actually outputs this minus 3 point blah, 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 and plus 3 point blah, blah, blah. This is not really humanly interpretable. So we do one operation here called softmax operation. That's one line of code on the logits, which translates it to sort of interpretable probabilities. So in the end, we get a probability. The sentence is probably positive. Okay. Then everything put together just in one code cell looks like this. And we get this. Or in the pipeline, this is what I showed in the beginning. Everything is even faster, or more efficient in terms of writing amount of code. And it looks like this. Okay, now the same also for GPT model. It's actually very similar. The main difference is what the model outputs. As I said before, we give it a text. For example, today I finally believe we can. I believe we finally can. We can finally, and then blah, blah, blah. We wanted to complete this text. And here we use GPT-2, which was still open source. And then we tell the model to generate a text for us. We give it the token IDs as inputs. These inputs were created by the tokenizer, which received this text as sort of an input. Okay, let's look at what the output of the model is. Today, I believe we finally get to the point where we can make a difference in the lives of the people in the United States of America. This was something that GPT-2 now completed for us. What's happening internally when we do this? So let's essentially run the same, only that we tell the model when we do the generate, we tell it to output a bit more. Output scores, which are probabilities, and output a dictionary with more information, so that we can look a bit more inside of the model. And then we get the outputs again, we print the outputs. And now this looks confusing. So now we get lots of numbers. And I want to briefly show you what these numbers roughly mean. Now we have first GPT's vocabulary composed of 5,000 tokens. That's how many words or subwords it knows. They're all numbers with or vectors with 768 numbers. We can also look at the entire vocabulary here. So it's just again a list of words. So this is how GPT-2 knows language. Now we can look at the token love, which is at position 18,000 something. And we can access the number here. Actually, how did I do this here? So here, let's look at the code for this. Maybe we go in the model and we load the weights. So this is a bit different, the naming than for BERT. We look at the position and the vocabulary 18,000 something something. This is love for GPT-2. And we print the first 100 numbers. This looks like this. So this is love for GPT-2. While the classifier produced probabilities of classes, you know that GPT-2 produces probabilities of words. So it actually does not predict just two probabilities for positive, negative. Actually, what GPT-2 does, it predicts a probability for each of the tokens of its 50,000 tokens that it has in the vocabulary. So for each of these tokens, it calculates a probability and then chooses the most likely one. And so let's look at it like this. So this is the tokenized input IDs at the beginning. This is our text. Actually, these are the output IDs. The output are actually also token IDs, which we can then decode to a full text. And now the original prompt was this. The actual task that the model knows is predicting the next token. So we look at the first token that it predicts, where the output, the first thing that GPT-2 actually predicts is again a sequence of numbers like this, where the most likely of these numbers, if we can translate this to probabilities, is token number 651, which is the word get. The second most likely token is 2. The third most likely token is the, and that's how you, in the end, generate this this text. You can look at the code a bit more if you understand this more. This is the same principle for all generative models, if it's GPT-4, Llama 2, or whichever. Okay. So now, again, we'll take a short phase of asking questions, and you can ask any questions that you might have about what I've just showed in the chat. Or you can also answer these questions here for yourself. So there's a bit of sort of self-work exercise. And if you have any questions about this exercise, also post it in the chat, and I will respond in a few minutes. Or, well, I'll respond actually relatively soon. Oops. I think I'll wait for 1 minute or so, see if there are questions, and then try and respond to them. Okay, I'll start responding to the first question. The first question is, if GPT has these probabilities in the background, how is it that the output of GPT-4 often differs to the same input text? That's a good question. The way that I've done this here, we can actually see this in the code. In the beginning, I told it, do sample false. There are different ways of making the model randomly sample, or with different sort of sampling algorithms, which tokens it should choose, and to create add more creativity and also more variety to sort of the product ChatGPT. OpenAI does not take the most likely token, but it takes one of the maybe, I don't know, 10 or 50 most likely tokens. That's one thing they do. They also do something that's called beam search, where they actually don't necessarily directly predict one token after the other, but they predict a token and then they predict the second one. And they recalculate, when they've predicted the second one, they recalculate the probability, or they look again at the probability of the first token and see if this sequence of 2 words makes sense, or maybe a different second token would make more sense. So I have essentially different way of sampling to adding more variety to the outputs. Can somebody share the slides? Yes, someone can maybe put the slides in. Someone did already. Cool. Okay. Cool. If there are no other questions, again, here are the tasks that you can probably also do later or at home to think a bit more about this. One more question. Hi, Sean. Can you talk a little more about the BERT max of 512 tokens and how to handle longer documents? Yeah, that's a relevant limitation that I've actually not mentioned yet. And these models can only process 512 tokens. The main reason for this is the so-called quadratic complexity of the attention mechanism. I've shown before that for every new token, or for every token, it multiplies its vector with all of the other tokens, which means the more tokens there are, the more multiplications there are, which means when there are a lot of tokens, much more multiplications need to happen. And this becomes very computationally expensive, which is why the older model have this limit of 512 tokens, mostly for computational reasons. The newer models, now the standard, especially for the generative models, is more 2,000, 4,000, 60,000 tokens. This will increase because of optimizations that people have done. So you can also find models on the hub with a longer sequence window. For example, the UL2 model from Google. This one is a very good model. It's very big. So these models are always big, but this one can process 2,000 something tokens. But there's others too that can do this. Okay. Models change answers frequently, especially in different numerical math questions. How can we, or can you talk about this? Yeah. So this for generative models. We will also talk a bit more about this later. Actually, for maths problems, I would not really use these models because they're not at all designed to solve math questions. So it's something that people like to do because it's sort of a big limitations of these models. If I wanted to do maths, I would use use a calculator, or two, there's something newer that works better, I think, that is making the model write some code that does the calculations for you. And I think this is more reliable. For example, OpenAI supports this with their functions now. But that's simply a limitation of these models to do directly the maths. But making them write code, Python code that does the maths, that works better, I think. Okay, I think we will need to continue because we're a bit behind. But great that there are so many questions. Let's look at the agenda. Oops. So we were now inside of transformers. Now, in a way, we come to the main part, fine-tuning our own BERT model, and then we'll come to the break. For this, one general note on this before we start going into this notebook on fine-tuning a model, especially for the beginners in the group. As I said before, you don't really need a computer science degree to do these kind of things. The requirement is, I think, not really formal education in computer science or math or something like this. The main motivation is motivation to persist and sort of knowing how to find solutions and wanting to learn and wanting to find solutions. And the skill of finding solutions to something that you don't know yet is really, in a way, the most important skill. Where sometimes people sort of say, and I also thought this sometimes, so am I actually good at programming, or am I just good at Googling stuff? Which is, I think, in a way, true. This a very important skill to build is just knowing how to find out solutions, programming solutions to problems that you don't know how to solve yet. And they're the thing that I think also really experienced programmers do. And you should also do, especially as a beginner, is to learn how to Google or now learn how to chat GPT. If you get an error, just copy it into Google. Someone else has probably had the same error before and you will find a solution. Since 2023, this became even easier with ChatGPT, which is actually extraordinarily good at debugging and helping you to learn and understand concepts you don't understand yet. I do this too. And especially as a beginner, you should do that too. So also if you run these notebooks, there's an error message, copy it, put it into ChatGPT, put it into Google, and you will find an explanation for where this, what the problem is. This has never been easier, especially since ChatGPT. Okay, fine-tuning a BERT model. Let's go into this, the third notebook. I will share this new screen. Okay, fine-tuning a BERT model. Here's a link to the paper that I mentioned before. This is partly based on the paper that I wrote. Okay, now we want to first actually kill this process here. So it's just a CPU. Oops. Okay. So for this, select a GPU if you want to run this yourself. Go on runtime, change runtime type, and select a GPU here. I take this one to make parts of it work a bit faster, but everything will work with sort of a free T5 GPU. And then let's start. So we'll first install the things that we've installed before: transformers, accelerate, the datasets library, which is also from HuggingFace, which is there to load and process datasets, and Optuna, which will be something we'll probably not talk about later, but there are examples in the notebook, is on hyperparameter tuning. So it installs this. Then we load a few libraries, pandas and NumPy. I think you've heard this in the introduction to Python. So just for processing data, we will, this is important, set a random seed. This random seed, you will see this pop up throughout the code. This ensures reproducibility. There are certain random things that happen in these models, and also when we maybe sample training data, this ensures that the outputs will always be random, but it will be the same random thing. So you will see the same result as me. Now, we will go we will load a data set. Here as an example data set, I've taken a data set from the so-called manifesto project, which is a cool project that annotates party manifestos from all over the world. Link to the website is here. And this is a specific data set or a specific subpart of this data set where we have sentences from party manifestos. I show what the data looks like. It's a bit messy, will be cleaner later, where we have a numeric label. So for textual version of the label, so this is, for example, other. It's actually, that's all other, that's a bit annoying. For example, like this. Another label is military negative, because a task of this, or in this data set, is to identify whether a text is positive towards the military, negative towards the military, or not about the military. And interestingly enough, this is actually a bit of a coding error, so this is a bit of a mistake. But then here we have the original text, which was annotated as military negative. So for example, and introducing a strict licensing regime to prevent sales of weapons and military equipment to undemocratic regimes, blah, blah, blah. This is a sentence from a manifesto from the United Kingdom, from some party from the United Kingdom, with the original sentence that was annotated and the preceding sentence and the following sentence. This is the structure of the data set. And this will be our task, a three-way classification task. Now I've put some code here. If you want to run this notebook on your own, you can uncomment this and run this yourself. Connect to your own Google Drive, specify a new path in your local Google Drive in your cloud directory. And then you can load a CSV file, for example. If you have a CSV file and you want to load something, you could copy paste this code, you just need to adapt it a bit. In this case, we just downloaded data from GitHub. Then we'll do some sampling to make it a bit smaller and to make stuff run a bit faster now in the session. We take 1,000 training texts for training, 4,000 for testing. And this is what this code does. It samples some 1,000 for training and 4,000 for testing. Now let's inspect the label distribution here. The label distribution is very imbalanced. We also had a question about imbalance before. This is a general problem with pretty much all real world data. So you don't have nicely balanced data where you have exactly the same amount of text for each class, but it will look more something like this. In reality, there's actually way more imbalance. I've just balanced it a bit more, where only a few texts are about where the military is seen negatively. Then there's more about where the military is seen positively. And then the majority is about texts where it's actually nothing about the military, it's about something else. And this stark imbalance is actually more realistic also in the test set. Okay. Now we do one pre-processing step here, which is it's always better for the model to have a bit more context. So what we do here is we take the original text and we concatenate it with the preceding text and the following text. So we just say preceding text plus following text plus text that was annotated plus following text, which just gives the model a bit more context to interpret the sentences in context. Then we'll delete a few columns to make it a bit more easier to read. And then sort of the training data set, the clean training data set looks something like this. Label, textual. This is actually not necessary. I just put this in there to make it easier to read. And then the text. The main thing is this numeric label. Okay, now we load a transformer. And this is daunting at the beginning because there are 300,000 different models on the HuggingFace Hub. So which one to choose? So there's many you can choose. I've given you a bit of guidance here, just general things that I recommend. The original BERT is a good model, but it's outdated. In pretty much no case would I use this model today. It's just old. There are smaller versions of it that are efficient and almost as good. I called DistillBERT. And then the model that I mostly use is a model from Microsoft, which is called BERT version 3, which is very good. It's similar to BERT, has a few updates, works essentially the same. It's just better. So I would pretty much always use this one. Can also, if you have more compute or want more performance, you can take the large version. So either base or large. At the end, this always indicates the size of the model, these indicators. And if you have multilingual data, you can use this one. This has an M in the beginning, as I mentioned before. This is a multilingual model. Also, my models, the multilingual models, are based on this one, and the other models are based on this one from Microsoft. And they've open sourced this. It's on the hub. You can use it. Okay, so now we load this. What does this look like? We define the model name with this identifier, which you know by now. We load the tokenizer. Again, auto tokenizer from pre-trained. We specify the model name. And to use a fast tokenizer, we specify the maximum length. You can reduce this if you have shorter texts, and then training is a bit faster. But we keep this to the maximum. I've talked about this before. Of 512 tokens. And then, so what it's doing right now, it's downloading this. Then we will, one thing that we do here is we map, that's what this code does, the numeric label, the 0, 1, 2, to the label words that make it easier for us to interpret the outputs later. That's what this code does. Oops. And then we load the model itself like this. Then we do one more thing that is relevant. You always need to also put the model on a device. That means we're now running on a GPU, the V100 GPU, but we could, this GPU also has an internal CPU. If I didn't do this, then it could happen that we do the entire training actually not on the GPU, although the GPU is activated, but we do it on the CPU. To make sure that it doesn't happen, we go to model.to, so we write the model to the device, which we define here. And here it's either the string CPU if you want to run a CPU, or CUDA, which is essentially means GPU. It's language from NVIDIA, from the GPU creator. So CUDA means GPU essentially. Okay, now we've loaded the model, put it on the GPU. That's important. Now we tokenize the data. We had data frames before, which is probably more common to people, so Excel spreadsheet kind of format. Now we put this into the HuggingFace datasets format. We import the HuggingFace datasets object. We create a dataset dictionary with a train and a test split, where we load the training data frame and the test data frame. Then we define a tokenizing function, which loads the tokenizer, takes the text and tokenizes it. This is a function which we then map over the entire dataset. Then we remove a column that's unnecessary. Let's actually run this. So it does the tokenization here of the 1,000 training data points to 4,000 test data points. And then let's look at what the dataset now looks like. We have label text. This is what we had before. Now we have new things. We have the ID. This just means ID. I actually don't even know what the X is for. It's just a unique identifier for each data point. This is actually easier to explain like this, maybe. Let's look at one example. So we have the label, which is a number, the text, and ID. So this was row number 71,000 in a data set, apparently. Then we have the input IDs, which are the token IDs, the token identifiers that we talked about before. Token type IDs and the attention mask are not so relevant. I've put an explanation here. So here's everything is explained again. I'm actually going to skip over this now. You can read this up if you're interested. It's not so relevant here. Okay, now we've tokenized. Now we set the training arguments or the hyperparameters. Here is a bit of blah blah. You can read this if you're interested. We set a training directory where the outputs would be saved. Okay, now this becomes a bit more complicated, and this needs a bit of practice. The different sort of parameters you can choose for training the model. In Hugging Face, so this is called training arguments. We'll look at the first few, and the rest I've also, for all of them, or most of them, I've written an explanation here, which you can read up. So training arguments. First, epochs. This determines how many iterations over the entire training data set we will do. So we have these 1,000 training data points. We can iterate over this once for training, which would be one epoch, or we can iterate over it for, let's say, 7 times. That's 7 epochs. One iteration, one epoch is one iteration over the entire 1,000 training data points. The learning rate, maybe first the batch size, this one. The model doesn't see the entire data set at the same time. It actually couldn't load that into memory, but it sees the text in batches. A common batch size is, for example, 16. So at each training iteration, it sees 16 different texts. It samples a random set of 16 sentences from the 1,000 and tries to learn from these 16. This is one batch. Then it moves on to the next 16. That's the second batch. The batch size determines how many texts are in one batch. After each batch, the parameters of the model are updated. Let's actually look at this. It's also explained here. So after each batch, the parameters are updated. The rate at which these models are updated is the so-called learning rate. This means we can give it a number. For example, the number is always written in this notation. This essentially means 0.00002. That means essentially colloquially speaking, the model parameters are updated at a speed of 0.0002 after one batch. I could increase this number. I could increase this to 0.02. Then the model would learn more, meaning the parameters are updated more. The problem is that this could screw up the parameters because after each batch, it only learns from one batch, and we don't want it to learn too much from these 16 examples. We want it to learn a bit from these 16 examples and also a bit from the next 16 examples, which is why we only updated a bit. Now, the exact number for this, there's no objectively good number. So this is a hyperparameter where you can play a bit around with different values. This is just a general value that works well in general. Okay, and then there's other hyperparameters, which I'm actually not going to explain now. They're a bit less important. They're explained here. You can read them up. Okay, now let's go to the metrics. I actually also need to run this so the rest works. Did I run the previous thing? Yes. Okay, metrics. Now we also define a function how to calculate metrics, and the best one for this is scikit-learn. That's sort of, I think, common standard, which pretty much everyone uses in Python. For different metrics that can be calculated, there's a function that essentially calculates these metrics. I always test on different metrics: accuracy, F1 macro and F1 micro, precision recall. I've also explained them here with an easy to understand example. We'll come back to this later. So just in general, know that the easiest one to interpret is accuracy. That just means if I have 100 texts or 1,000 texts, and the model gets 900 of the 1,000 right, then the accuracy is 90%. So that's just the share of examples that I got correct. This is sort of the easiest to use metric. It's not a good metric for imbalanced data because I should mention this. Let's imagine we have 1,000 data points, and actually out of these 1,000 data points, more than 900 are one class, for example, not about the military, which will be the case in reality. That data will be drastically imbalanced. A very simple model that only predicts always, in 100% of the cases, that no text is about the military, it's always about something else, on a data set where that is realistic, where most texts are actually not about the military, will have an accuracy of above 90%. Because it will always get it right when it's not about the military, but it will be a very shitty model because it always predicts the same thing. That's the main disadvantage with accuracy. And I like the metric F1 macro, which sort of takes this into account. And it's explained a bit here. We maybe come back to this later. Okay. So let's run this. And oops. Now I accidentally started training already. Okay, we initialize the trainer. Now it's training. We have a trainer from HuggingFace, oops, where we input the model, we input the tokenizer, we input these training arguments, the hyperparameters that we gave it. We give it the training dataset and the evaluation dataset, our test dataset, and the function for calculating the metrics. So all of the things that we did before. And then we just go trainer.train, and then it trains. And this looks like this, where what I did here is I made it sort of process one batch, then process one epoch. Now it's doing the second epoch. You see the progress. So it's almost on the second epoch. Now it stops. Now this is all the training data set. Now it does the evaluation on the test set. So it doesn't learn anything here. It just predicts. It just tests how good it is. And here we always see the output numbers. So we see that after the first epoch, the model has a very high accuracy. That is because the data is very imbalanced. So here it probably mostly predicted it's not about the military. For the F1 macro metric, which is sort of more sensitive to imbalance, the score is much lower. And this one is actually a better score. This one is what it has learned after the first epoch, how good it was. The first iteration over the training data. Now the second iteration, it actually got a bit worse. On accuracy, it got slightly better on F1 macro, but only very slightly, which means that it has understood the minority classes that are not so frequent a bit better. This is especially visible after the third epoch, where accuracy still remains the same. So this metric is sort of meaningless. On F1 macro, also balanced accuracy. I probably should talk about this one. It's also a bit easier to understand, where each class has the same weight, the same importance, whether it's a majority class or a minority class. Here it gets progressively better as it learns more to predict all the different classes and not only the big majority class. So now after each epoch, it learns a bit more. And it can also, and that's what we start seeing here, get a bit worse after epochs. Let's actually see what the output of this is. And when it gets consistently worse, here's still getting better. Now, after 5, 7 epochs or so, it will not really be getting much better anymore. It will even get worse. And this is then called overfitting, where it's looked too much specifically at the training data, because all it does during training is only looking at training data. And then on stuff that it has not seen, it gets worse and worse because it knows so much about the specific training data and tries to identify some patterns that only count for the training data, but are not useful for the test data. And that's when it starts getting worse. So too many epochs are also not good. So here, for example, it got a bit worse again, and so on. Okay, cool. So this is almost done training. Another thing to note here is that I think one could have the impression that it's sort of training a model takes super long, takes days. You see that it certainly does not take days. It actually takes only minutes, because we are not doing pre-training here. The model is already pre-trained by Microsoft. Microsoft invested weeks or months into pre-training their model. We are just fine-tuning it, which is way faster and actually quite efficient. And now we're actually done training the model. And it has a decent balanced accuracy as well. Okay, now it's just loading some stuff, and now we're done training the model. One more relevant thing to note, there is what I've used is a training data set and a test data set. In reality, what you should do is use a training data set, a validation data set, and a test data set, especially if you do hyperparameter tuning. So if you do play around with different learning rates, for example, or different batch sizes, you should always do this on another random sample of your data, and then choose the best model there and only evaluate on a test set at the very end. The main reason for this is that if you evaluate on your, or you do hyperparameter tuning on your test set, then you're essentially you're choosing the specific hyperparameters that are good for your test set, but you don't know if they will be good for other data it will see in the future. Which is why this hyperparameter tuning, we never want to do that on the test set, because we want to be sure that it generalizes well, so that the hyperparameters that we've chosen will work on any unseen data, not only a specific test set. Okay. Now, there are some examples on doing inference with the model. I think we can skip this. So this is now if you wanted to do some predictions with the model. One thing that you can see here, if you run this later, is actually the output. So here you see the predictions on the test set, and then you can see also where it did things wrong. I don't know if I also put this here. So here you can inspect a bit where I put the true label and then the predicted label, and you can search for examples where I was wrong and try and see why it got these things wrong. So you can inspect this if you want. And then there's a few things we don't have time for now. If you wanted to save your model, there's code for this here. If you want to upload the model on the hub, there's also code for this here. And there's also stuff on hyperparameter tuning, which I also skip over now. In the end, what I actually don't really do hyperparameter tuning anymore with my models, because I've noticed that it doesn't make that big of a difference, but takes a lot of compute and time. So there are a few good hyperparameters like the specific learning rate that I've shown, which just works well in general. But if you wanted to, there would be code examples also for hyperparameter tuning. Now, I've talked a lot, and now I want you to try and answer your questions again. There are, again, like before, a few things that you can do now if you want to, a few questions. You can rerun it, look at the code in the notebook again, try and answer these questions in your own words. And any questions that sort of come up now or in the coming 3 or so minutes, put them in the chat, and I will try and respond to them. I'll wait for maybe 1 minute and then I'll respond to the questions. Okay, so let me start responding to the questions. First one is, maybe I don't know if you see the chat here. It's maybe also good for people who watch this later on so that they see the chat, but maybe you don't see it via Zoom, I don't know. With traditional models, we use a split of 80-10 or 80-20. Why do you use so much in the test data? Well, having more test data is always better. And that was actually mostly for demonstration purposes. Yeah, that's mostly for demonstration purposes. And because it's so imbalanced, I want to have enough examples of the minority classes. That's another relevant reason why I did this in this case, to have enough examples for the minority classes in the test data as well. So I can be sure that it works well on the imbalanced class and the minority classes. The next question, how do you deal with class imbalance when fine tuning? So you can deal with this a bit during pre-processing by just downsamplings of majority classes to make it a bit more balanced. Then during fine tuning, there is a way of changing the loss function in the model so that the model takes into account errors of that are on the minority classes more than when there are errors on the majority classes. So I don't have code for this right here, but if you Google or ask ChatGPT, how do I change the loss function to give higher weight to minority classes, you will find some code. Also, Hugging Face's code on how to change loss functions. That requires a bit more technical skill, but that would be another way of doing it. Then next question. If I want a binary classification like positive and negative, how balanced should the data be? I've read that for hate speech analysis, that there should be a threshold of how much data should be hate. Is there a rule for this? Yeah, it's also a good question. I don't know of a specific rule. Just the more balanced, the better. That's not a helpful statement though. What I would do during data collection is trying either with simpler or with more advanced methods to specifically find more data for your minority classes to get it as balanced as possible. You can either do that with keywords, so specific keywords that might indicate your class like hate. There's something called active learning. I will come to a tutorial, or I will have a link later on with a tutorial on active learning that I did for Agila for this annotation interface, which is also a solution for this. So we'll come back to this later. To try and make it as balanced as possible. And that is a general challenge. Everyone has this challenge. What happens if I see that the results are not good? Is there a way to correct the model's mistakes, annotate them and run the model again? Or does this mean you need to annotate more data in general? We will come back to this. So in 40 minutes or so, we will talk exactly about this. Data cleaning and annotation. How can this session be helpful for students starting a degree in computer science, I suppose, the first year? How can it be useful? Hopefully try to understand transformers more. I suppose the main useful thing is copy pasting code and trying to run it yourself, read through the slides, see what's interesting and Google more stuff afterwards. I think I missed this one, which model we choose in our specific case, 1 to 7, which is the decisive metric. I'm actually not sure if I understand the question. Maybe you can post a clarification. Next question, I would like to have a suggestion. Okay. I'm just reading because we get more and more questions. I'm going to select a few because we need to move on to the break actually. What I actually would suggest now is that we are now essentially at the moment of the break. I will continue. Oops. I think you now see the slides again. I will continue answering these questions, but this was the main part on fine-tuning BERT. You can continue asking questions. But to roughly stick to the schedule that we have, I would say that we do a break now of, let's do 10 minutes. So we do a break of 10 minutes where you can grab some water, walk around, stretch a bit. I will also stretch a bit. You can continue reading the notebooks, and in 10 minutes we'll be back. I will just continue answering a few more questions, and then in 10 minutes we'll continue with the session. But let me continue answering some questions. I'll just see if there's anything else. So to respond to you, Wang, could you explain more the point on train validation split? I'm not sure if there's something you copied from the notebook. So in the end, especially for the hyperparameter tuning part, you split the data into these 3 parts: the training data set, the validation data set, and only the validation data set you will use in a way as the test set during hyperparameter search. And then only one at the very end, when you've chosen the right hyperparameters, you do the testing on the test set, so on the 3rd split. Okay, well, I think I'll give you a break now, and we are back in now, let's say 8 minutes. Thanks a lot for all of these questions. That's really cool. I wasn't sure how many questions there would be, and it's great that there are so many questions. So see you in 8 minutes. Great. I think we can continue. And that was, I think, a very good first half of the workshop. I was really impressed by all of the questions that you had. That is really cool. And that shows that it's interesting and useful for you, which I'm very happy about. And now we can continue. So we had the break, and I hope you could get maybe something to drink, go to the toilet, move around a bit. And now we'll continue fine-tuning. So we left a few questions open at the end. And we will now rerun essentially the same notebook, looking at a notebook that looks very similar. So if what we just did was too fast for you, or you still have questions that were not answered, just ask them again. This notebook that we look at now will be relatively similar. Okay, now we will fine-tune again a BERT model, but a slightly different variant. This BERT NLI model, these zero-shot models that can also be used for few-shot classification. For this, we go in the next notebook. Oops. In the next notebook. So there's the fourth one, again, via the GitHub repository for tune BERT and then underscore NLI. This is this notebook. And a brief note why this is so zoomed in. I hope that this is zoomed into the right amount. Maybe it's a bit too zoomed in. That helps, makes it bit difficult to sort of see everything. But it's also important to be zoomed in enough, because I know that some of you might look at this on smaller screens, or if you're in a developing country, maybe even on a smartphone. So that's why I try to zoom in quite a bit. And I hope that's the right amount of zoom. Okay, now we have talked about, or we fine-tuned BERT base. We've also talked about this NLI task before in the theoretical part, and now we put that a bit in practice. And I want to start with this by sort of sharing a metaphor that is, or a scenario that helps you a bit understand how BERT base works and how these universal models that I mentioned in the beginning, how they work. So imagine the following scenario. You have a text annotation task where you want to classify each text in one of three categories: positive towards the military, negative towards the military, or not about the military. So that's what we just did. You don't have enough time to annotate yourself, so you walk around on campus and pick a random person, and you lock them into a room to do the task for you. Maybe annotating 10,000 texts or something like this. You do not explain the task to that person. All this person finds in the room is 1,000 papers with text written on them, these sentences that we saw before, and only a number, 0, 1, or 2. That's the only thing they find in that room. You've not explained the task to them, what they're supposed to do. That's the only source of information, but you expect them to understand this task purely on these 1,000 annotated texts. Then you come back 2 hours later and ask the person if they've done the task and if they've understood the task that you wanted them to do. Now, would it be reasonable to expect that person to have understood the task that you want them to do? And I think it's obviously stupid. Most people would not have understood the task that you gave them because you didn't explain the task to them. Weirdly enough, this is exactly what we do with BERT base though, because the only thing BERT base gets as an input is the text and the numbers 0, 1, and 2. So these label text columns in the beginning, this was actually only for you to help for understanding. This is not what BERT base can process. The only task BERT base knows is this masked language modeling thing. And it then needs to look at these texts and find some pattern that helps it optimize or solve this task. And imagine if you as a human were given this task, 1,000 texts with only text and numbers written on them. Would you understand the task? Probably not, or you would need a lot of text and it would be complicated, or you could totally misunderstand the task and learn something that's actually totally unrelated. These would be validity problems if the model seems to have found some patterns, but has not really understood the task. It just found some random patterns in the text because you did not understand, explain the task to the model. And this is what we do with BERT-based. A solution to this problem is to use models that can also process instructions, so that besides these numeric labels 0, 1, 2 and the text can also process instructions, like you would give them to a research assistant if you wanted them to annotate something. You would also give them sort of the verbalized labels, so explanations of the labels, to make it easier for the research assistant. And this is also what you can do with some models. One type of this model are these BERT NLI models. Another type of model are the generative models that we look at later. Okay, so with this short introduction on why this is relevant, let's start running this notebook again. There will be a lot of repetition, which is, I think, helpful though for understanding, because we do it in the same scenario. We install the relevant packages that we installed before. Then we load some stuff for pre-processing. We set the random seed to make sure that we always get the same results. We load the data again. Here again, if you wanted to, you could later on also load your own data. We do our train test split, or like downsampled for the purpose of this tutorial, so that's faster. We have the same data imbalance as before, so it's exactly the same data. This is what this random seed ensured, that this is exactly the same before. If you looked at the data frame. Now comes what the specific part about these NLI models. Now I've explained when I showed the PowerPoint slides that with NLI, you verbalize your labels in hypotheses. So what you would do is you would click on the codebook for a task, or you would think about a codebook for a task, look at the definition of different classes, and then, oops, okay. This is the codebook, for example, for the manifesto corpus, where every label is explained in plain language. For example, military positive has this definition. This is also what research assistants see when they annotate stuff. So we look at this to try and understand the task ourselves. And then we formulate hypotheses about this for each label. So we have the label military positive, where now we formulate a hypothesis. In this case, for example, the quote or the text is positive towards the military, for example, or in favor of military spending, defense, military treaty obligations. Then we have military negative, and for this, the hypothesis would be the text is negative towards the military, for example, against military spending, for disarmament, and against conscription. And then the last one, the quote is not about military or defense. So this is stuff that I've formulated by looking at the definition in the codebook. Now we run this, and the cool thing is that we can give this as an input to the model. Now we pre-process the text again. We only do one slightly different thing. Before, if you remember, we took the preceding text as additional context, because this is also something that the annotators see. They don't only see individual text, individual sentences, but they see also the surrounding text to help them annotate stuff. So we take the preceding text, the original text, and the following text, concatenate them. We only add some additional guiding language that helps the model understand the task, or to help it focus on the text that we actually wanted to focus on, the original text. So we also tell it, or we format the string as preceding text, then the quote, we open quotation marks, then we put the text, and then we close quotation marks, and we say end of the quote. This is why I formulated it like this. The quote is positive towards the military. So the model is supposed to focus specifically on this text segment. This is what we also can do by verbalizing the label. So now let's look what this looks like. Now we need some additional processing of the data, because also NLI models can only predict 3 classes, which is always true, false, or sort of neutral. Or people use different names for this, also entailment, not entailment, or entailment, contradiction, and neutral. This is also the only thing that this model can do. But we can translate, as I've shown this in the previous slides, any task, any classification task into an NLI task. This is explained a bit more here. And this is a function that sort of does this for the training data, where we, just in brief, for each hypothesis, we take all the text where the hypothesis is true, give it the label 0, which represents true for an NLI model. Then another thing that we also do, we give it an equal amount of false texts, where we give it a few texts where we give it the wrong hypothesis. So it learns to distinguish between right and wrong. And then we append this all together. This is what this function does. And now we have a newly formatted training data set. This looks like this, where we have the label, the numeric thing that the model can process, 0. Then just for us to make it easier to understand, this means true. Then we have the hypothesis. This code is negative towards the military, and for example, against military spending, for disarmament, against conscription, and so on. And then we have a text where this quote is supposed to be negative towards the military. Let's actually look if that's the case, or if it's noisy. Emergency relief in this situations of armed conflict should be carried out by civilians and must be clearly distinguished from any military activities. Okay, so in this context, this hypothesis is true given this context. This is the task that this model learns and this model can do. And we give it also the same text with a wrong hypothesis. So one time this text appears twice in the dataset, probably also with the wrong hypothesis. So it learns to identify wrong things as well. Okay, so this is what this looks like. You can also inspect this yourself if you're interested. Then we do something similar with the test set. There, let's look directly at the output. For the test set, for testing, we have every text. For this, actually, almost need to zoom out. Every text 3 times, actually. 3 times every text. So this is always the same text, where we test each of the hypotheses, hypothesis 1, hypothesis 2, hypothesis 3. Only one of them is true. Only one of them is true. The other ones are false. And what we hope that happens during testing is that when we feed all of these texts into the model one after the other, it will say that this one is the most true one, while these ones are false. Then the model would be good. If not, that would be a mistake by the model. So this is how we need to slightly reformat the test set if we work with this kind of task. Okay. now we load, this is essentially the same as before. We load the NLI model. I zoom in more again, maybe. Let's maybe put this to, can I change this? No. We'll load the NLI model, same as before, auto tokenizer from pre-trained, model from pre-trained with our identifier. That's just one of my models, could be any other NLI model. We determine what device we're on. To see that we're on a CUDA device, that means GPU. We put the model to this device to make sure that we're actually running the training on a GPU and not on a CPU. Okay, now we've loaded the model. Now we do the same with tokenization as before. That's essentially the same as before, just the tokenization is slightly different because we need to tokenize both the text and the hypothesis. Then we tokenize this entire text. This is a function. We map this function over the entire text, which does the tokenization. And then we remove some unnecessary columns. Let's look at what this looks like, then it's easier to understand. So now we have a data set dictionary with a train set and a test set with now more than 1,000 rows of training data, because we've given it sort of the true labels, but also wrong examples. So we've in a way also implicitly augmented the data set where text can appear 2 times with wrong texts. This doesn't always add up to 2,000 if they're minority classes. And then also we have a much bigger test set. This is actually a disadvantage of this approach, is that the test data also gets bigger. So testing or inference time takes longer. So the making predictions takes longer, especially if you have a lot of classes. That's a disadvantage of this approach. And advantage is that you sort of artificially augment the training data. Then we have the same, did I run everything here? Just to make sure that I ran everything. One example looks a bit the same as before. We have the label, for example, 1, prepared text, hypothesis. These 2 are actually irrelevant. I just let them there for you. Each text has, again, a unique identifier, the token IDs, and then token type ID and attention mask, which are not so important. Okay, and now, again, same thing as before, we need to set training parameter, training arguments, hyperparameters. Here I do essentially the same before, same learning rate, same batch size. One difference is warm-up ratio, which I set a bit higher here, because the model has already more prior knowledge. And so the assumption is that in the beginning, I don't want to overwrite too much knowledge with a high learning rate, which is why in the beginning, for the first 25% of the training data, the learning rate is lower and then gradually increases to this maximum rate. This is what the warm-up ratio does. So you start with a lower learning rate and then this goes higher. I also copied an explanation below. And just for the sake of this example, I trained this model only for 2 epochs. That's faster and illustrates the point I want to make. Okay, let's run this again. Here again, explanation of the different hyperparameters, the different metrics. The calculation of metrics is a bit different here because we need to process the outputs a bit differently again. This is done by this, but I'm skip over this. Again, the explanation of the different metrics. And now we can start training again. That's exactly the same as before. We have the trainer. We have the model, the tokenizer, the training arguments, the training data sets, our compute metrics function, and we'll start training. And this is sort of now exactly the same as before. It's very fast. It's done probably in 2 minutes or something like this. While it calculates, let's look at, well, the following code is again just how you would then use this if you don't want to do training, but if you want to use your model to make predictions. So you would, like before, define your hypotheses. And then in this case, I'm using the zero-shot classifier pipeline, where we load the model. Once the training is over, the model, this object will be overwritten with the best model that came out of training. And now then we can immediately use it. Or we could also specify some other pre-trained model from the model hub. And then we can start making predictions with this on any other text. Okay, so now in this case, what you will notice during the training time, if you remember in the beginning for the other model, the F1 macro and the balanced accuracy, they were significantly lower with the first two epochs. Here they are higher. The main reason for this is that this type of model already started with more prior knowledge, with both the language knowledge and the task knowledge it had from NLI, because it's a model that was already trained on NLI data. So it needs less epochs, less iterations over the training data to become good. And we only do 2 evaluations. And after this epoch, it will be roughly the same or slightly better than the BERT base after 7 epochs. Actually, the overall accuracy is a bit lower after the first epoch, because it tends to less overpredict the majority class and more the other classes. And now after 2 epochs, we're already slightly better than the BERT based model. Okay, and now we've trained a model, and we could make predictions with it. Just in these few lines of code, we can take an example data frame, and then look at the data frame, look where it has made mistakes, and that's how you would see the outputs. Okay, this is pretty much the same as before. Here also same code for loading and saving models. That's the same. Hyperparameter search is slightly adapted, but in principle the same. And that was already this. So this is a different model, but most things work the same. So now the same time as before, the same thing as before. Let's take just a few minutes for you to reread the notebook. Think of questions. You can read these questions that I posted here for you. You can try and think about them and put any questions you might have in the chat. I'll give you a few minutes to, maybe 1 minute to think about potential questions. Also, if there was a question I didn't answer during the previous session, don't hesitate to ask it now. Okay, so I'll try and respond to the first question. I was wondering how the model can be fine-tuned to maximize specific metrics, for example, recall rather than accuracy. That's an interesting question. I have not really thought about this much before. I think one way of doing this would be through hyperparameter search, where I need to talk a bit about hyperparameter search. This is in here. Let's skip over most of this code. So in hyperparameter search, you test different hyperparameters and see what is best at the end. Now, the definition of what is best is up to you. In the example code that I've given here, I've defined that the objective that the hyperparameter search is supposed to optimize is supposed to be F1 macro. So this is based on Optuna. That's a library that sort of searches for hyperparameters that are that automatically selects hyperparameters that optimize the objective that you give. So here you could specify, for example, recall. Then you can make it run 10 times, and then it will select the hyperparameters for you where recall is maximized. So that would be one way of doing it. That's the main way I can think of now. Can you summarize the difference between BERT NLI and BERT in an implementation point of view? So I'm not entirely sure what you mean by implementation. In terms of the architecture, it's pretty much exactly the same. The only difference is, if you ask like this, you probably know a bit more about this. The only difference is the classification head on top of the model. So both are, so for BERT-based model or deBERTer version 3 model, same amount of layers, same amount of everything. The only difference is the classification head, which for a normal BERT model, if you fine-tune a normal BERT model, the very, very last layer of the network is actually for BERT base, the masked language modeling head, which is useless, which is why it's deleted. And you randomly re-initialize a few parameters that do this new prediction task for you. So in terms of architecture, the normal BERT would be a BERT model with a 3-way classifier at the very top. The BERT NLI, we don't delete anything. We keep its task knowledge, and we keep the classification head that is already tuned for NLI. That is, I hope that responds to this question. Is the notebook shared? Yes, it's shared. I will put the GitHub in the chat again. So all of the notebooks are in this GitHub repository, and this is notebook number 4. And another question. How the difference in on text length. NLI models work better with shorter text. So this is a limitation. But any transformer works better with shorter text. That's actually a general limitation of these types of models. If your task, but I would tend to always give more text. So if in your use case, if you're hesitating between only giving the title or title first paragraph, I would always give it more information. I would, in general, I would think of the model, although it's not at all the same, but I would think of it a bit like a research assistant, like or a mechanical Turker, a person who works for you. What would this person require to do a task properly for you? And people will be able to do tasks better with more context. So the tendency is to give it more text, I would say. And then if it's full text, then if the articles are too long, you will need to truncate. So you will need to cut off, and the library also does this for you. Okay. I think we will move on. One more question. You cannot generate. So the question is, can we embed NLI with BERT in order to generate sentences by specifying emotions? So it cannot generate anything, it can only classify, but you can use it to identify emotions. Then you would formulate a hypothesis. This text is, I don't know, has a positive emotion or has a negative emotion. That's how you would do this in general. Okay, then I think we should move on to the next section on data-centric AI. So what we've now done in all of these sections, so this was essentially just a bit of a rehearsal of training another model. This was all about model optimizations. Now, another thing that is extremely important but neglected is the data for training these models. And I always find it surprising how much noise and how much wrong data is in widely used data sets, which is why I want to talk a bit more about data-centric AI, about data quality and how to clean data in the first section with CleanLab, which is a library for automatic data cleaning. So this is our next notebook in the GitHub. GitHub was also just posted in the chat. So now open this notebook. Okay. And for those who started later, you can always click on the notebook. And then there's a button, open in Colab, which will automatically open it in Colab. Might give you a warning whether you trust the source, and you can trust the source. I didn't put anything mean into the notebook. Okay. Data quality and data cleaning, data-centric AI. What is data-centric AI? So I think it's a pretty established fact that machine learning researchers spend most of their resources on optimizing their models and spend too little time on thinking about their data. So they spend hours of labor and also on GPUs, which are quite expensive, to find the ideal model architecture, or let GPUs run for days for hyperparameter search, which is also something that I did myself. And then at the end, after like literally an entire week of hyperparameter search on different data sets, I got a performance increase of 0.5%, which I would say that's not really worth it. That's not really relevant enough. And something that's really neglected is looking into the data. And sort of a small movement that sort of believes this and also creates open source resources for this. There's a data-centric AI movement. There's one professor from Stanford who also founded a company based on this idea, who really pushes this idea. And he says that companies need to move from model-centric approaches to a data-centric approach. Okay, now let's illustrate a bit what this means. There's a nice website called labelerrors.com, or you see label errors in widely used datasets. And these are from image classification. So you can also click on this yourself now if you want. So this is an image classification dataset where, for example, this image was classified as a yo-yo. The true label is golf ball. This was classified by a human. So if this is the gold standard you're testing your data set on, is a washing machine. And I actually wouldn't even know what that means, but apparently it's or mechanical Turkers say it's a bread maker. Or this is a bear. The true label is actually a teddy bear. Now, models trained on this kind of data cannot learn anything good, because if they get wrong information, they cannot learn anything meaningful. And that's the main idea between data-centric AI. And this is very widespread. So this data set has more examples, and we'll look at a few now. There are data-centric AI tools like CleanLab, a Python library that enables you to quickly identify label issues in just a few lines of code. And they also did a bit of research on this. I have links on this if you want here. They also have interfaces that you can use. I've never used these, but I'm using their library here. And there's actually more and more research also for large language models that data quality is more important than data quantity. And I put a few links here. Now, what types of label issues exist? First, there are just normal, simple label errors. So text is classified in a wrong category. That's simply a mistake. That's the stuff that I just showed. Then there can be more subtle issues like label overlap. So there could be an image or text that could be plausibly put in two categories. And this issue can have two potential sources. Either I made a mistake when I defined my codebook, when I defined the task, because I should have make the labels more distinct. This is avoidable. And another source for this can be that real world data is just complex, and sometimes the true response is just unclear. And this is unavoidable. And we'll see some of these ambiguities that are unavoidable later as well. And then another type of issue is out of scope texts or data, where text does not fit in any of the provided categories or labels, which also often happens. And most of the time, data sets need but don't have sort of an other category. For example, if you have a sentiment classifier that can only classify positive or negative, I find that absolutely useless, because in the real world, most texts are neither positive or negative. They're just neutral. They're just factual statements about something. And that would be an out of scope problem. This is also avoidable when you define your task. Okay, so let's illustrate these things I have said a bit with concrete code examples. Here I'm actually running this with a T4 GPU, so you can do the same. Okay, we're loading transformers again, datasets, and CleanLab, which implements this automatic data cleaning stuff, and sentence transformers enables us to use a specific type of transformer. Then we load lots of different packages, and I give a general overview of how this CleanLab package works. It works in two main steps. We fine-tune a model on our noisy data. The model then gives us predictions about how certain it is that a text belongs to a certain class. We repeat that several times to get different predictions with different parts of the data as training data, to get different sort of probabilities for text from the model. The main reason for this is, or the main output that we need here, is a probability of sort of a simple model when it's trained on noisy data. Then CleanLab has implemented some algorithms that take these probabilities and try and find patterns in this data where the model is so uncertain that it's unlikely that the actual data is true or is correct, or it finds instances where it recognizes that there are two labels where the model is very often sort of unsure which one is correct. So label overlap, and then it flags these as potential issues. We will do this in two main steps. I will not properly explain this here. You can read this up later a bit more, because it's a specific implementation of transformer that takes this as text, an input as a text, and gives a vector as an output. and then we train a logistic regression on this output. So we're actually using a logistic regression here as a model, and with the features that it gets is a transformer or transformer output from a sentence transformer. But this could be implemented in different ways and not so important now. What is relevant now is CleanLab provides a function called health summary, which gives us a general overview of problems in our data set. And then I'll just do some post-processing here in that function. This is for general issues in the data set. And then if we want to identify issues for specific or individual texts, I've written another function that sort of returns this. But I'm going to skip over this. You can read this later if you're more interested. What is relevant for us now is that we're going to download a data set. This is an emotion detection data set that's been downloaded several thousand times and can identify 6 different emotions: joy, sadness, anger, fear, love, and surprise. We'll download this with the HuggingFace dataset library. So we go load dataset, have this identifier, which we can do find via HuggingFace if we go to the datasets. It's the same as with models. We go on a dataset and then we can copy this. This is always the identifier. Then we load this. We do a bit of post-processing, delete some columns, other column, and then the model we load look like this. We have training data with texts and labels, so very simple, with 16,000 training data points, validation test split from this data set. It's actually very imbalanced, so we mostly have joyful sentences and very few surprise sentences. And this is an example for the data. Then we will do the analysis where we take all of the texts from the training data set and embed them with our sentence BERT model, which we then use as an input to the dataset health analysis function that we've defined above. And the main thing we're going to look at is the output that comes out at the end, where we will have an overview of the label quality overall of the dataset and potential overlapping classes. So what it now does and takes a few seconds is training several logistic regressions on this data, making predictions of it, and trying to identify things that don't seem quite right. Okay. Now, this is the data frame, so the table that shows us the overall noise issues in the data. So let's actually look at the right more. So we have the class text, so the class in words. Surprise has a label quality score of 0.5, which is relatively low. So it's not a class where there's more noise. While sadness has a label quality score of 0.85, which is the highest. So there's less noise according to CleanLab. So this is not all entirely true, but this is of a rough indication. So there we have a first general overview of how noisy the different labels are. Then we can also see overlap between different labels. So we see that the class joy has strong overlap on 800 text with the class love. Anger has overlap with sadness and so on. So this is something that you would probably expect, and this identifies this automatically. Now we use the CleanLab cleaning function to identify issues not on the level of the entire data set, but on individual texts. And I will actually run all the things that come afterwards as well, because this always takes a bit. So again, now it's training a model and identifying the uncertainties of the model for each individual text. Okay, so now with 16,000 texts, we have sort of gotten rid of, or we've identified that around 7,000 have issues. And let's actually now look at this a bit more. Let's look at those with the lowest label quality. Let's maybe look at this one first. So here in this row, very low label quality according to this package. We have the sentence, "I feel super bad about it," which for some reason received the label joy. The system says it's probably more sadness or something like this. So this is just wrong. Let's look at the next one. "I feel their pain and it's not pleasant." For some reason was labeled as joy. The system says might be anger. I don't know if that's anger, but it's definitely not joy. "I did not feel sympathetic as a narrator struggled through her low-income life." For some reason was labeled as love. Definitely not love. Maybe it's sadness, maybe not. That's also an issue. So not all of these things where the system says it's low label quality are really problems, but it identifies a surprising amount of just bad quality data. And then you can get rid of it, because we can either use this label quality as a threshold for just deleting some data or discarding, or the label issues column based on a more specific algorithm that they implement to get rid of some of the data. Okay, so this was the first example where you really see where there are real issues in these types of data sets. That was one data set that I wanted to show. I also prepared a second one. This is a topic identification class data set, which is on Yahoo Answers and topics. This one is actually a bit big. It's like, I think, 1 million texts or something, which means that it takes a bit longer to load. But here it's essentially the same. So I can already start speaking over this, where it will load. It will do exactly the same as we've seen before. We'll load the data, fit it, and then we'll see several issues in this data set. I think actually, given the timing, I think it makes sense to just directly continue now. Actually, I'm just going to skip over this, because this is just a second illustration of the same thing. And that was already it for data cleaning. So this is code that you can copy paste yourself and identify issues in data sets that you might find. We'll directly move to maybe 2 minutes of questions if you have any questions on this. You can look through the notebook again, ask any questions you might have, and post them in the chat. I'll wait a bit longer to see if you have any, give you time to read and see if you have any additional questions. And then I maybe start directly responding to the first question. Yeah, what you're describing, Husnain, is actually a relevant difference that I didn't really explain properly. There's a difference between multi-class datasets or tasks and multi-label datasets or tasks. I've always now talked about multi-class, where we have, let's say, one text, 3 classes, and according to my task, each text can only have one label and none of the other labels. That's multi-class. Multi-label means that one text can have multiple labels. So I have 3 classes, and out of these 3 classes, theoretically, one text can have all 3 of them, or only 2, or 1. So this is, yeah, it depends on how you set up your tasks. It depends on your definitions and so on. You can handle this with the NLI models by, let's go back to the very first notebook. When I run NLI, where do we have this? We have the flag, we have the zero-shot classification pipeline. We defined our classes like this in our text. Here I can say multi-label, true or false. If I say multi-label true, then I allow the model to have that one text can have multiple label at the same time. If this is false, then every text can only have one label. This only works with the zero-shot classification models. You can also do this with like normal classification models, but then you need to specifically fine-tune them for this. And I've actually not done this before. In my use cases, it's always needed to be one class. Well, I'm sure there's documentation on this in the Hugging Face documentation. Okay, next question. Yeah, how much noisy data is okay? Is there a threshold for amount of noisy data? Good question. I don't know. So I think you need to test this yourself. I also noticed some limitations with CleanLab, especially if you have strong minority classes. It tended to be uncertain about the minority class and often think that minority class labels are wrong, which can be an issue because you already have little data for it. That might be an issue with these automatic methods. And I think it really actually depends on the task. There's no right label quality issue of always 0.5 or something like this. I think this is also supposed to make you interact with the data and find which one seems right for you. But there's no one size fits all solution. Okay, then I think we directly move to the next notebook actually, which is also still about data-centric AI. Only this time, oops, we're not there yet. So that's what we just did. Now we go to notebook number 6, annotation interface Agila, where we will look at an annotation interface and also how you can interact more with data and also correct issues in the data yourself. So that's notebook number 6, again, via the summer school. We go here. I just posted in the chat. Q also already posted it, so perfect. Cool. Data annotation with Agila. Now, these things that I've showed you, they allow you to clean data in code. It can be easier to have this in an interface that just allow for more functionalities. And there are several interfaces like this: CleanLab, Galileo, Label Studio, or Agila. You can click on them. I've linked on them. They all have different advantages, disadvantages. We'll use Agila in this case. Main reasons for this is it's free and directly configurable via Python and fully open source. I also contribute a bit to them. I contributed a tutorial to them on active learning. I mentioned that before. And I just like them in general, so I'm using this as an example. But you can compare the different annotation interfaces, and they might have different advantages and disadvantages. Actually, kill the GPU here. There's several GPUs running. Okay, so a brief overview on Agila. So it's an annotation interface specifically for NLP. So if you work with images, others are probably better for you. They have several demos hosted on the HuggingFace Hub, because HuggingFace also provides a way for other libraries to host demos. Let's actually look into this. So this is their website, or their space or organization space on the HuggingFace Hub, where they have this so-called space from hosted on HuggingFace, where they've hosted their interface. And you can log in with a simple username, Argilla, and password 123456. So anyone can log into this and play around with this. You can also do this in your browser now if you want. And they have different data sets with different examples for different tasks, how you could annotate them. So for example, for text classification, we could go in here, and then we see the annotation interface that's now running in the cloud somewhere, hosted by HuggingFace or Amazon Web Services, where we see the text. Then we see the labels that were linked to this text. And now I can start annotating this data. I can sort the text by, for example, I want to look at everything that was already annotated in a specific category. I want to correct this, look at non-validated or validated things, so things that are already annotated or not. One cool thing is also, so these things I've just said, you could sort of also do this in an Excel file. Something that you cannot do in an Excel file is, for example, you might have this text, and now you might say, this is a text that's particularly difficult, or it's an edge case. I want to find similar text to this one. And here you can click on Find Similar, and then it will find similar texts. So this is something about technology and Windows XP or something, and it will find similar text to this, which will make it easier for you to work on edge cases or more quickly annotate text that you might find particularly important and you want to find similar things. And then they have other functionalities I can't cover now. This is, for example, for text classification. Same also exists for token classification, where I can want to highlight words and classify them, for example, for named entity recognition. I might say that this is an organization. I can highlight text like this, or if it's not a good thing, I can also delete it again, and so on. I can also do this for generative tasks, where I have a text, and for example, the model produced a summary, and I want to correct the summary, so I can correct the summary somehow. All of these different tasks can be done in this interface. Okay. It's just a quick run through because we don't have that much time. Now, this is the interface part. Now, how do you get data into this interface? So you get this free interface. Now you have your own data, and you want to get your data into this to annotate it on your own. The first thing you need to do, either you can run this locally via Docker, and there's also documentation for this. What I'm doing in this tutorial is I'm deploying my own annotation interface on the HuggingFace Hub, which you can do if you click on this button. Here I can create a space. I can name this space somehow, test 3 or something, 2. Then I click on Docker on Argilla, so the pre-made template that they have for running the code. Then I get a free CPU for hosting this. Then I can choose to have persistent storage or not. I don't want to spend money on this, so I can just choose storage that will be deleted after a while, which is sufficient for this now. I can add a bit more security details, like an API key or usernames. I'm not going to do this now, but then you can already create this space, for example, a public space. And then this gets built within a minute or so. And then you have your own annotation interface. I'm not going to wait until this is done. It takes like 1 or 2 minutes, but then you have your own annotation interface hosted online with a link that you can send to everyone. You can set your own passwords and only let specific people log in. Okay, so we have the space hosted online. Now, how do we get data into this? We can do this via Python. We install the relevant packages, the same as before, and this time Agila as well. And I'm also installing CleanLab again, because we're again using a data cleaning example. We load different packages, download the data set. And then we do essentially the same thing as before. We use one of these sentence transformers to process some of this text. We train a model to identify these uncertainties. And then, and this is a bit new, so the above is pretty similar to what we did with CleanLab, because this also works based on CleanLab. Then we load Agila as RG, and then we add records to Agila. And this works by doing something like this, rg.textClassificationRecord. And then we define the text, the prediction of a model in this case, because we're testing CleanLab here and its predictions. We're adding the predictions from CleanLab. We're adding the actual annotations that come from the dataset created by someone else. We also add the vectors, which enables the similarity search that I've shown before. And then we've prepared the data in this records format, which we can then upload on Agila. So it's doing this now, processing this data now. Then something that we add here is to these records, we want to identify label issues. This is a function that is integrated from Agila, so we can directly get this from Agila. It identifies label issues, and then we can look at them. Okay, now we need to link what we are doing in this Google Colab, so essentially a server hosted by Google, to our space that we've just created. For this, we need the link to our space. And here I actually use a space. So this one is actually done now. This is the one I've just created. But for simplicity's sake, I'm going to use one that I've already used before. This one. So we can now open what we've just created. This will then look like this. We can then click on embed space. And here is the link to the space that we've just created. We can copy this, put this in the URL here. And then we could specify a key so that only specific people can log in, but that's not so relevant for us here. And then we upload our records to the hub, to the thing that we've uploaded, that we've just created online. So here we name the dataset dataset cleaning 2, which so this is uploading it now. And then after a few seconds, so this is this is the space I've prepared, but could be the one that I just created. Now here we have the dataset data cleaning 2, updated 2 seconds ago. It's actually still updating stuff. It's still uploading stuff. And then we can start annotating in this interface with our personal data. So let's actually reload this. Now, 2 seconds ago, it's finished uploading all of the data. Now we can click on dataset cleaning. And we can start cleaning. I also like sorting this by score so that we see the things that it's sort of most likely to be wrong. And now we can correct the data, essentially. So I have the text, I feel blessed, so darn good, so darn good talent right here. So the annotation, the official annotation says love. The system says this is probably wrong, this might be joy. It's probably a bit of an edge case. I would not say that this sort of entails love. So I would correct this and say that this is actually joy. This is the same. Oops. Repetitions. Another text, I feel amazing after every thrift trip I go on and have so many small amount of time with my ideas of bliss. Some weird text that the system says indicates surprise. If you read it, I'm not sure if that indicates surprise. Might also be more joy or something else. Maybe this is sort of an unclean text I want to discard, so I click on discard. I'm not going to do this much more now, but this is how you can now clean your data. Okay, and everything that happens here now is on the model hub. Now what I can is on in this interface, but now I want to also download this. So this is what these few lines of code do. I load the data set, again, with the updated annotations that I did into the records format. Then I transform this into a data set. And now I have a data set that I could use for training a model. Or I could write it to a CSV file or an Excel file and send it to someone or do whatever I want with it. Okay. Now, this was a brief overview of data-centric AI. Now I have prepared exercises for you, which we will do a bit more briefly because we do not have that much time left. Let's maybe collect questions in the chat now. Any questions you might have on this, post them in the chat. If you don't have specific questions, I would recommend that you now take 1 or 2 minutes where you click on this link, you open the Agila UI demo space, and you start annotating stuff a bit yourself. You just start playing with the interface a bit yourself, and you annotate some stuff to get a feeling for this. The really interesting thing that I learned when annotating data is that it's actually harder than you would think. There are more edge cases than you would think. And then I'm less surprised if models do weird things, because I know more that the training data is also weird often. And that's the main thing you can get out of this exercise and out of playing a bit with data annotation yourself. Or you can probably also do this after this workshop. Let's just see if any of you have questions. Does Label Studio, for example, have a similar Python interface, or is this exclusive to Agila? I think they don't have it exactly like this. They are more, so in a way, a more mature commercial product where to properly test it, you need to subscribe to something and set up an account, I think. It's not as configurable and as hackable with Python as Agila. This depends a bit. Label Studio is, I think, actually quite good, especially if you do image stuff. I think they seem good, although I haven't used them before. The others, Galileo does not have this. It has a Python CLI, so it can do something with Python, but not, well, the documentation is definitely not as open source. CleanLab Studio. So CleanLab has its own annotation interface, and there I haven't tested this yet, to be honest. They have this cleaning library. I'm not sure if they have that for their interface too. Any other questions? Otherwise, I think it's actually good if we move on to the next section. Let's close this. So this was a bit of a detour into data-centric AI. Now we are, oops. Now we have still the important part of actually fine-tuning generative LLM, which will be pretty much the exact same thing as for the other two. You'll see how similar this is. So let's open this notebook now. The number 7. And I'll also go a bit more quickly on this. You'll see that this is pretty similar to the previous training runs that we've done. So here's just an image of the many different types of models there are in the generative models. I will not talk about this. It's just there's lots of them. I think that's the main thing I can say now. We'll do the same thing as before. We'll install the same libraries. One specific one that can be helpful is bits and bytes. They help you run models in a quantized way, make them smaller. I think actually in this notebook, I'm actually not even using this. But this is a pretty cool library that helps you run larger generative models, because the models that we're looking at now, they will be larger. Yeah, so this can be very useful for this. Then same thing as before, we load pandas numpy, set our random seed, load the same data, the same train test split. It will be the same distribution as before over classes, same data. And now is where it starts becoming a bit different again. So while with the NLI model, we verbalized our classes in hypotheses, for these generative models, we do that via instructions. I imagine that many of you have heard of this before. So in this case, we take our previous task and we reformulate it like this, as a question actually. Which of the following categories fits best for the quote above? A, military negative. The quote is negative towards the military, blah, blah, blah. B, military positive. The quote is positive towards the military, a few examples. C, the quote is not about the military. And then I tell it only answer one of these options, A, B, or C. And then I say answer, colon, and what I expect the model to do is to output either A, B, or C, which I can map to these labels. Now I need to do pre-processing. Oops, I need to run this. Pre-processing, where I do the exact same thing as with the NLI model, concatenate the preceding text with the original text with the following text. And then I add the instruction at the end, so that the instruction is also within the data. Then I'll show an example for this in a second. Then what I do is I take the numeric labels and translate them to the tokens, so the strings, the tokens that I want the model to predict, because the model will be a model that can only predict tokens, next token predictor. So 0 corresponds to 1, military negative, and so on. Then I get rid of unnecessary columns. And now the training input looks like this. I have my prepared text, which has the entire text. I've simply appended the instructions. So here's where the question starts. Also line breaks, which are not visible here. And then the correct label here would be A, which stands for military negative. This is what I want the model to predict, not a number, but a token, A in this case. And this is the same for all of the data. This is the main difference in terms of pre-processing if you work with a generative model. Now, things will be very similar again. So again, I need to specify the identifier to a model. Here, I actually take a not so big model that makes things faster. Is a T5 model, which is a good generative model from Google. It's originally from 2020, but was recently sort of trained on a lot of additional data and then became quite good. That's the so-called FLAN T5 dataset. You can find this on the Hugging Face Hub. Then we add a few parameters, which you can ask questions about if you're interested in this later. Here again, a few parameters that are specific to the generative models. So here I tell it how many maximum new tokens I want it to generate. For our case, 2 is sufficient. We don't want it to produce more. We don't want it to beam search. A temperature, which you might know from OpenAI. This is also in these open source models. We set that to 0. That makes it more deterministic. We only want the most probable token, and we don't want it to sample from the top 50 token or something like this, which is why we say only the most probable one token. We tell it to output a few additional things. And then we do the same thing as before. Auto tokenizer, auto model for sequence to sequence language modeling. So this is essentially text generation, sequence in, sequence of text in, sequence of text out. We add these parameters that we've just defined above into these models. And then they're ready for training. Then we only need to do tokenization, similar as before. The main difference here that we need to make is that we need to tokenize both the text, so the text column from our training dataset, as well as the labels, because the labels are now also text that need to be tokenized. So we tokenize both. This is what this function does. And we need to be careful that the maximum input length is still 512. And the labels also count towards this limit. So I'm just reducing this by 16. Okay, and now I've tokenized this. Now the same, it looks very similar to what we've seen before. So I'm not going to show this again. Now we need to set hyperparameters again, which again, except for these additional things, and don't hesitate to ask questions about the additional things later, is essentially the same as before. We have a learning rate, we have the batch size, the epochs. This is very similar. It's almost the same. So we define all of these things. One more function for handling memory. That's not relevant now, though. Now for generating the metrics, we need a slightly different function for creating the metrics, because the output will be token IDs, which we need to decode first to translate them to the label tokens, so ABC. So this is what this code does. But then we can simply use scikit-learn again like before. This is the same code as before again now for calculating these different metrics. Then a small last thing is there's a specific data collator for these kind of models. That's sort of a function that loads the data into the model during the training process. Well, it's simply this one line of code. And now we can define the trainer. Here from transformers import sequence to sequence trainer, so text generation trainer. We specify essentially the same things as we did with the other models, and we start training. And that's interesting here. So I've used actually a base T5 model. So also this one is actually not huge. This one is also relatively fast. So here one epoch is actually pretty fast. One epoch is done in like 20 seconds. because generative models don't have to be huge, especially these specific type of models, T5, so-called encoder decoder, they are better with smaller size. They're actually quite good. But you could do the same. It would look quite similar if you were doing this with Llama 2 or with another model. Only if the model becomes bigger, then you have a bigger headache with hardware. So it's done the first epoch. Now it evaluates on the test set for the first time after the first epoch. And here what we will also see is, because the model, again, as a reminder, it's a universal model that has already existing task knowledge. It already knows how to predict tokens. So it can be better with less epochs. It's actually not really visible here, though. It will become better with a few more epochs. A general message. While we're training this. So here I use a generative model to do a classification task. In general, that is actually not a good idea. So I'm just doing this for illustrative purposes, so you see what the instructions are like and so on. If you have a classification task where you have these classes that we discussed, it's actually more efficient and will be better if you use a normal BERT model. So a model that is specialized in classification. There you're wasting compute and making your life harder than it actually needs to be by using a model that is designed for generation and therefore needs to be larger to be good, has a huge parameter overhead to be able to do what it's supposed to do, which is generating tokens. But all of these capabilities you don't really need for a classification task. So if you do classification, it's actually easier, or actually better, more efficient to take one of the BERT models that I've shown. But now you could also fine-tune this model with this code for other tasks as well. If the label column that I showed were, for example, a string of text, so not IBC, but a string which is a summary of text, then you would train it to summarize text. You would need to use different metrics, though, because then these kind of metrics don't work anymore. Because what you get as outputs is unstructured text, and you cannot calculate accuracy for this. I can also talk more about this if people have questions about this. So it's now doing the training, is gradually getting better. So we don't necessarily need to watch this until it ends. This is also essentially the same as before. We see the outputs. You could look at the mistakes that it made in this data frame. Here again, you have code to load the data set or to save the data set and also upload it. But I think since I've shown this notebook several times now, just in different variants, I think this is enough. So what we do now, we do that shorter though. We just do a question answer round where you can ask any questions you have about this specific notebook. What you can do afterwards is just try and rerun this notebook and change the instructions a bit. Think about how differently you can formulate the instructions so that it might be better, it might be worse, and you will notice how sensitive it is to the formulation of the instructions. Okay, so this was essentially how you fine-tune one of these models in not that many lines of code. And you've also seen that through Hugging Faces, everything is relatively standardized, so everything looks relatively similar, also compared to the BERT models. Are there any questions about what I've shown so far? So I start answering the questions. The first, what about something like llama for sequence classification? Actually, for sequence classification, I'm actually not sure if that exists. It might. If HuggingFace implemented this, maybe not. That would probably not be a good idea. So you could do this, but for a llama model that is trained to predict words, it does actually exist. Okay, someone implemented this. So to get, you can compare this. I haven't compared this myself. I would expect the smallest llama is 7 billion parameters. You can train this on this data set. And I imagine that it will have similar performance with 7 billion parameters compared to the BERT v3 model, which has just, I don't know, 300 million parameters. So it's only a fraction of the size. The main reason for this is, or it might be a bit better, but not significantly better. The main reason is that, as I said before, these models are made for predicting next tokens. They're not really tailored to classification. The pre-training task they've been trained on, next token prediction, is not very efficient for learning how to classify text. We know this empirically from the literature. So if you have equal size, the generative model like llama will definitely be worse. And then you get better if you make it bigger, but you get a lot of other headaches that you don't really need, I think. And I also just quickly Googled this. For these llama-like models, there's also a tutorial on HuggingFace. I actually don't know what kind of model they use there, but you can also look at this. There's also, they use GPT-2 there as an example. So you could also look at this. A question about data cleaning and removing certain characters that are useful, though, that carry meaning. So how much should we clean data and remove certain symbols? So given your question, you might have probably used other classifiers before, and then featureized text like TF-IDF and remove stop words and punctuation and so on, where you would then remove something like a minus or hyphen, as you mentioned in your question, like E minus commas. With older models, you do this kind of pre-processing where you remove this. With transformers, you do not remove any words. So you don't do any pre-processing like this. You just leave e-commerce with a minus as is. And the model will be able to process all of them and will understand that E minus commerce, the minus is relevant for what the two different character sequences mean, E minus commas. So actually, for the transformers, you don't do more than the tokenization. You need to do the tokenization, but this will automatically take care of everything. Okay, so we will do a bit longer. We're not quite there yet. I've discussed it with the organizers. We can do the sessions a bit longer, but we'll not do this much longer. The remaining thing that I have is mostly thinking about also yourself, about risks and opportunities for these models. So we'll maybe do not more than 10 minutes longer. Now we've learned about all of these different things, how to fine tune them and so on. It's also relevant to think about different risks that can happen when you work with these kind of models. And what I've thought of before, but we can do this actually much shorter now, is that I'm going to show this like this. I'm going to post this in the chat now. And where's the chat? You also have this on the slides. This leads you to this notebook where you can think about different risks that are linked to the language models. So I will talk more about benefits in a second, and I think they're pretty obvious. I've listed some of them here. It's not exhaustive. I've put a bit of literature here on different risks that are associated with these models. And what we will do, actually only very briefly now, and then you can also do this later on more thoroughly if you want to do this more. Think about different risks. You can put your name or nickname in here and just put a bullet point of different risks that you can think of that are linked to these models. I think they're widely discussed, so I didn't put any examples here. The main reason for this is that you can build a lot of really cool stuff with this, and that's why I like talking about this, like sharing this. But you can also really misuse it, and we should be aware of this. This literature shows you more information about this. So you can now think a bit about this, put some thoughts in there. If you have any other questions, you can also put them in the chat. We only do that for 1 minute now. Great. I've also sort of answered a question in writing. I really invite you to think more about these different risks and look at the literature here. Now let's move on to sort of the final exercise, which is also sort of an exercise we will not do now, but it's a good sort of transition to sort of the end of this of the session. That is to reflect on your own project. Actually, I should post the link to this also in the chat. So this is another notebook in the chat, also in the slides. I feel like this is the most valuable ending exercise, which you should do after the workshop for yourself, is to reflect a bit on your own project and on what you're interested in, and a problem or a research question that you want to solve, you want to find an answer to, and think about what are the required tools that I need to answer this research question or solve this problem. What do I still need to learn for this? Any other open challenges or questions? And then try and think of sort of a relatively simple but challenging example for a project that you could do. And I've sort of put 2 fake examples in here to give you an idea for this. The main reason why I recommend this is that I have learned everything that I know about this essentially by doing, not by reading so much about it, this as well, but mostly by sort of being interested in a specific problem, wanting to solve a specific problem or having a specific research question, and making it into a small attainable project that you can solve maybe within a week with the current knowledge that you have. And this, if I were you, would be the next step that I do after this for our workshop. Think about this kind of project that you could do with all the code that I've given to you. And this is a bit of an exercise that if you had less questions, we would have done this now. But since you had many questions, which was very good, we are slightly over time, so we're going to skip this now. But you can think about this for yourself, which should, I think, be very valuable for you. Okay. Then this is actually the end of the session. So we've gone through all of these different things that you see on the slides now. The general overview that has hopefully shown to you how simple it is to use them in the beginning. Hopefully intuitive explanation of transfer learning and this theory behind why certain models are better than others. And then fine-tuned our own transformers, 3 different variants, always with the same notebook, which you now can take yourself and try and rerun and change and adapt to your own data. And we've done a little detour into data-centric AI to also make you focus a bit more on the underlying data and how important it is to be rigorous about this, maybe even really equally important as doing model optimizations or something like this. Okay, so that's it essentially. As I said, if I were you, now you have some resources from me, and you also have the entire internet. Since a few months, you also have ChatGPT to explain stuff to you, help you debug, and so on. So it's really never been easier to build something with transformers, to build a small solution to a small problem that you have, try and answer a small research question in an attainable little research project that you have, something that would have taken really a team of people with years of experience a few years ago. You can do that relatively quickly today. And I hope that this code that I've provided today will be helpful for you. If you have any questions afterwards, there are some contact details. You can follow me on LinkedIn or on Twitter or X or whatever. And I hope this was useful for you. And I wish you a good rest of the day, wherever you are. And I say bye-bye.